Welcome, everyone. We got a little bit of a late start, but we're going to try to stay as close to the agenda as we can today. So I just want to welcome everyone to the International Center for Integrated Systems Conference on Vaccine Risk Assessment. My name is Michelle. I'm a volunteer at the center, and by training, I'm a biologist and work in cancer diagnostics. Today is the eve of Diwali, the Festival of Lights, and perhaps one of the most auspicious days in the Indian calendar. We did not look at this on the calendar when we chose this day. In Indian mythology, there are many descriptions for Diwali. It is said that Diwali marks when great warrior Rama returned victorious after defeating the evil Ravana. It's also a great time to start things to do. New things to give and forgive, awaken ourselves to truth, unite and unify, prosper and progress. So the gods smile upon us today as we begin. Our center's goal is to use systems thinking and objective understanding of complex systems so we can go beyond pro and anti-vaccine, beyond left and right, beyond pro-vax, anti-vax, and identifying real problems for pointing all of us in the direction of real solutions. This is why we invited people of all backgrounds, all viewpoints, and all perspectives on this topic. This is not attending on either the pro or anti-side, have already made up their minds, and it's hard to use those who are not open, particularly to science, to see the way the world is, not how they want it to be. So I believe that the workshop today will help us get to the heart of the vaccine issue. We have a very compelling framework to share that will hopefully arm each of you to build bridges of understanding. Let me review the agenda. There are 4 points. We will begin with the keynote address, Dr. Shiva Ayyadurai, after which we will have our first session on vaccines and bioinformatics framework led by Dr. Prabhakar. In this session, Dr. Prabhakar will take 30 minutes to present, then he will take feedback from the working group for 30 minutes, after which we will open up to questions and comments from the observers. So the working group are these folks, our honored panelists, and the observers is everyone else in the audience. And we handed out these little cards for you to write your questions on, and then we'll have a volunteer that comes around and grabs them from you. And for those of you watching online, you can provide their questions and comments through the Facebook page. So once you folks fill out the postcards? Index cards, sorry. We'll pick those up, and then Dr. Prabhakar will choose some to answer at his discretion. Just write Q or C on the top left corner, and that way we'll know if it's a question or comment, or Q and C, so that we'll know quickly when we read these. Like I said, we're in a tight schedule, so it'll just help us to manage if it's a question or comment. All the feedback and comments will be documented as part of the public record. Dr. Prabhakar, also the facilitator of the session, will choose some of the comments at his discretion and share with the group and get comments from the working group. In session 2, Professor Debbie Nightingale will provide a presentation on engineering risk assessment, after which we will proceed in session, as we did in session 1, to the working group interaction and the observer feedback led by Dr. Shiva. Finally, before we close, we will take 15 minutes to summarize and provide next steps to move forward. After we close, after this event, anyone who wants to gather, we're going to have a meet and greet down at the Summer Shack right down by the T station. So given how fast this will go, I'd like to now thank our volunteers before we forget. Mike Mosca, Jennifer Bennett, Richard Giorgio, Andreas Arminez, I'm going to check that, sorry, Ram Subramanian, Mike Corbo, Louis Schenker, and for all of their help in making this happen, and to all the volunteers who have participated. Thank you. So without further ado, let me introduce Dr. Shiva Ayyadurai, MIT PhD, the inventor of email and world-renowned scientist who is recognized globally for his contributions to the field of personalized and precision medicine. Let's have a warm welcome to Dr. Shiva Ayyadurai.
Since we started late, I'm going to try to do this quickly, but anyway, thanks for everyone coming. I want to also thank Michelle. And I think we have about, how many, about a couple hundred people on Facebook Live, right? So sorry for the delay. There's always something that happens, but we'll try to speed this up. What I wanted to do was, the purpose of this conference is really to give a very different perspective on this entire discourse. And as Michelle said, this is really to move it beyond this vax, anti-vax stuff. And I think everyone who's taken time to come out here really is a commitment, I believe, to truth, freedom, and health. And I thought what we would do is first really, the key takeaways that I hope to convey to you is, what is health? You know, what is health? We all talk about health. What is the definition of health? And I hope everyone will walk away with a clear definition of what health is. And then how do we get to health? And then how does the discourse on vaccines, or lack of discourse, actually support how we can get to health? So first of all, how many people are from out of town here? Andre's going to want to, yeah. Yeah, so we have a lot of people out of town. Okay, so Boston, you know, when I came here, Boston's known as the center of science and innovation. Everyone's familiar with that, right? And my journey here actually has been a long journey. I was born in Bombay, India. Anyone been to India? You have these very wild scenes. India is a country within country within countries. In one scene like this, you can see probably about 20 centuries in it. But I was also brought up in a small village in India, and that village is a very different construct because you know, you have no running water, no electricity. It's very different than the cities. But in that village, my grandparents were poor subsistence farmers. My grandmother is actually also a traditional healer. So not only did she work for 16 hours a day, but on weekends she was the healer. Typically, women in most villages were the healer. You know, you didn't have medical doctors in there, so women typically learned a lot of these techniques of traditional medicine. So my grandmother could observe your face, predict what was going on inside your body, and this may seem like woo-woo to a lot of the conventionally trained Western people, but there's a whole science to this. We don't have time to discuss this, but in the Indian system of medicine, it's called Ayurveda or Siddha, and they don't use the words molecules or proteins or DNA, but they have their own language which describes how the body is a system. So I was exposed to medicine, but India also had a caste system. Anyone familiar with that? The caste system of India was very hierarchical. There were the so-called academics or the priesthood up on top, and then the kings and the warriors, and we were considered untouchables in India. So you won't find a lot of Indians like me. So I learned a lot about how systems of power also work. I was forced to do that as a young kid. My parents came here in 1970. It was quite interesting that my parents were able to get an education at a time when someone like my mom over there should never have been educated. So it's sort of a 1 in a trillion chance. But I had a deep interest in understanding systems, but also a desire to excel. This is an interesting article. When I was 14, this article came out in a little newspaper saying that a professor at NYU was going to offer 40 students a chance to go to NYU to study computer science. And I was one of those guys who was an overachiever. And I got selected, and I ended up going to NYU as a 14-year-old kid and studying computer science. And when I graduated, because of my deep interest in medicine, I started working while in high school at Rutgers Medical School. So I've been doing, medical research for a long time, believe it or not. As a professional researcher, I got a full-time job as a research fellow. We've talked to people who brought up SIDS, right? Sudden Infant Death Syndrome. Rutgers had some of the best data, this is disseminated on longitudinal data of baby sleep when babies were dying of apneas. So we did some of the earliest work applying computers to look at sleep patterns of babies and trying to predict when an apnea would onset. So I learned how to mix computing and biology as a kid, but I also learned how to build large-scale systems. Some of you may know this. When I say systems in those days, secretaries were really the powerhouse of communication. They used to build these things called a memo, right? To, from, subject. You notice inbox, outbox, folders. And in those days, computers, you could send simple messages, very short text messages. That's not what I'm talking about. But I was also asked to convert this entire system of communications. Anyone seen these? Pneumatic tubes into the electronic form. This is sort of the Ethernet before the pneumatic tubes were how you transported things. And I converted that system to an electronic form long before the military even thought it was possible. The military-industrial complex thought women could not do this. This is a quote from a RAND report in December 1977, basically saying that it was impossible to build a system like this because the users could not go from the typewriter to the keyboard. So it's a very sexist comment at the underline. But I call this system email. The only reason I called it email was the operating system allowed 5 characters. Email was created by the collaboration of great teachers, a great mentor, and a loving family. It did not come from the military-industrial academic complex. That's a big lie. So that's my mentor. Anyway, when I came to MIT, I was deeply interested. By the way, this was done before I came to MIT, all right? In Newark, New Jersey, by a 14-year-old kid. And on the front page of MIT, they listed 3 students who had done something of note, and I was one of them. And the president of MIT, and at that time, said, Shiva, you should copyright, because the Supreme Court did not understand what software was until 1994. And so I did it, and on August 30th, 1982, that 14-year-old kid, or 17-year-old American kid, was recognized officially as the inventor of email. Those are the facts. So when you see online people attacking my integrity, you can hit them with this. The fact is, email was not done at MIT, it wasn't done at Silicon Valley, and it wasn't done by some nerds at Raytheon. Okay? Anyway, so that was one journey I went through, as an inventor. But when I came to Boston, this is the scene of Longwood, okay? Anyone? I know Sylvia's from there. But you can see, this is also, Boston is known as the Mecca of medicine, right? This is another scene. I mean, you have the massive concentration of medical health care. So I was obviously, because of my other interest in health, was very motivated in this. But when I came to MIT, I was very concerned because the system of Western medicine looked at the body's parts, right? So if you go to a doctor with a headache, you could get 10 different people looking at you, right? You could go to a psychiatrist, an endocrinologist, a neurologist, you get sent everywhere. And it really helps the insurance model because each one of those you check off. And this is a result of that system, right? The healthcare is going to become 20% of GDP, right? 6-7 times more than even the defense spending. And what's even more interesting is if you look at the pharmaceutical world, year-over-year spending, as you notice here, in R&D costs, you would think the more you spend in R&D, what should you get? Better products. They're actually finding they're getting less and less new drug approvals. And this is around 2006. And by the way, this graph has not changed. So the pharmaceutical industry itself, Kendall Square, et cetera, is recognizing that their system of pharmaceutical development is also not working. It's very, very time-consuming, and it doesn't create efficacious drugs. This is a system of how we build pharmaceutical drugs. By the way, pharmaceutical drugs have very stringent standards. Interesting enough, vaccines aren't listed in those standards. Okay? We'll talk about this. But typically, this is how the process works. Someone here may discover a new compound. Then you raise some money, then you go do a bunch of in vitro research, which means in a test tube if you're trying to discover something for cancer. Then you go do research in vivo in an animal, and if you make it through that, during this process you go to the FDA and you say, look, I got really good results, I'm not killing animals, I would like to start testing on humans. That's called an FDA IND allowance. You file for that FDA allowance, and if you get it allowed, then you can go test on humans, phase 1, phase 2, phase 3. How many people know about this? Anyone? Okay, about 20%. This, and at the end of it, you get a thing called a drug that's gone through this testing. Phase 1 means small groups of humans. Phase 3 means lots of humans. Now, this is only for a single drug. What is a drug? A drug is a synthetic compound, okay? It's not an herb, right? It's not a yoga movement, okay? It's not, it's a single synthetic compound. The problem with this is if you look, $5 billion, lots of money go to it, and it takes about 13 years. At the end of this process, you only have 7 years to monetize it because the patent process is 20 years. So if it takes you 13 years to find a drug, you only have 7 years, which means what? You have to crank up the cost to recoup your investment. Moreover, as we'll talk about, it's not personalized. And 20% of the stuff making it to phase 1 make it out. So basically, it's a very, very inefficient system. This system is no different than, as we would say in engineering, how we used to build airplanes in the old days. You came up with a design, you threw the pilot in. If he crashed, you said, gee whiz, he crashed. And then if he survived, then you explain why that wing structure worked, okay? It's not really based on mechanistic understanding of disease. And if you further peel away into this, you'll find out that the real problem is academic research. So if the elephant represents, let's say, the immune system, which we're going to talk about, or it represents cancer or Alzheimer's, this is a story of the blind men. You know, Buddha tells a story about the king who brings in the 6 blind men, and he shows them the elephant, and everyone touches different parts. And each person has their own view of what that elephant is. That's called reductionism. That's a term that you'll hear. Reductionism is when you don't see the whole, you see the part, okay? So if you look at the entire immune system, you try to reduce its efficacy to something called an antibody or a white blood cell. This goes back to 1915. Or if you look at the environment, you try to reduce it to one variable called CO2. Or if you look at genetically engineered foods, you try to reduce it to something, okay? A single variable. The single variable model is a way to manipulate people, or you get a little glimpse of truth. And in fact, these blind men, if they actually ever got together, I don't know if you know the story, one guy thinks it's a snake, the other guy thinks he's touching a spear, you'd end up with something like this, okay? Has nothing to do with the whole, all right? Now, the interesting thing in academic research, if this is cancer, you get a Nobel Prize just for understanding one part. There's not an incentive for collaboration because of the way the tenure process is set up, and we can have a longer discussion about this. However, the good news is all of this really sort of started changing in an ironic way when the Genome Project ended in 2003. What you're seeing in this graph is, in 1993, when we started the Genome Project, we thought what made a human being different than a worm was the number of genes. So biologists who were very siloed, or they thought that complexity is a function of the number of parts. So if you look at this graph, we knew a worm in 1993 had about 20,000 genes. So we assumed, wow, a human being must have a lot more than that, right? So we assumed it was at least 5 times 100,000. You guys see what happens here? As the time goes by, they're not finding that many genes. And what happens in 2003, you only find around 20,000 genes. So I'll repeat, a human being and a worm have the same number of genes. Okay? But does that mean complexity is a function of the number of parts? No, because it's how things are interconnected. Okay? It's not the number of things, it's how things are interconnected. All right? So interconnection is what makes a difference. So this led to a field called systems biology. On one of my companies, I have a board member, a scientific board member, who had published this in Nature in around 2003 saying, look, if you're going to understand the whole body, so now Western medicine wants to understand the whole, it's not just the genes. You got to understand genes create proteins, cells. You have to. It's not a simple problem of the whole, but you have to actually understand the interconnections among these things. It's cells, it's tissues, etc. So this led to a very exciting field called systems biology. At this time, I was running another company to analyze email in a different enterprise. And I came back to MIT. My advisor, Forbes Dewey, said, Shiva, you got to come back, finish up your PhD. There's a really cool field called systems biology, and the National Science Foundation had put forward this big challenge, was could you mathematically model the whole cell? Everything all right, Andres?
Yep, we're doing great.
Okay. And so if you think about the human cell as a big chemical reaction, of interconnected chemical reactions. So think about it this way, okay? It's reactions within reactions, systems within systems. Now think about if you could model this, which means you could start doing experiments on the computer long before you did test tube, long before you went and killed a bunch of animals, because you could start understanding mechanisms. Is that clear? So this was sort of this grand vision of systems biology. And by the way, this is what's called a molecular pathway. You're going to learn a lot today, okay? If you read a paper in the scientific literature on, let's say, Alzheimer's, there's, or osteoarthritis, Prabhakar is going to talk about this later. There's 20,000 papers if you go to PubMed. If you type in, I think, vaccines, what do we find? 1.7 million papers, okay? And if you go read a paper, somewhere in that paper, someone did an experiment, and from that experiment, they found, chemical A reacts with chemical B to get chemical C, right? And this is called a molecular pathway. So today, the way we study biology is these little diagrams. If you take a biochemistry course, they'll draw a diagram, okay? These pathways were starting to become mathematical models, all right? Albeit small. And the issue was, could you interconnect these models together? And that's why I went back to MIT in 2003-07. I created a new technology called cytosol. What cytosol allowed us to do was to look at very complex molecular mechanisms, knowing that people were in their silos, let them do their silo stuff, but we would convert them to models, and we would create large-scale models of disease. And this was a revolutionary breakthrough because people didn't think this was possible. Even at MIT, the head of the department was doing maybe 50 different species, and he was leaving the field. We took a very different approach, an engineering approach. We didn't see it as a biologist approach. We said, imagine everyone in this room was individual biologists doing your thing and you're publishing. We would let you keep doing your thing, treat you almost as knowledge engineers, extract out the papers, extract out the mechanisms, and build a whole new technology to do this kind of model. And that was cytosol. What we realized that what we'd actually done was define a whole new way to do medical research. So instead of, notice I added the word S here, instead of just a compound, we could add multiple compounds. So you could test herbs. You can test combinations of herbs, which Western medical pharmaceutical system cannot do. And what we would do is mine the existing research, which means don't recreate the wheel, and model these very complex systems long before we even did in vitro testing. And by the way, this is how we build airplanes, right? Everyone's comfortable with this, right? You would never say, you didn't test that on a human, and kill pilots. You would say, did you do the modeling on the computer? Then you do wind tunnel, then you go. And this is a process how modern civilization works. Let me give you an example. How's everyone doing, all right?
Good.
Okay. So what I wanted to show you here is that so when we presented this was a big deal because people didn't think this kind of stuff was possible. So between 2012, we published a lot of papers, and to people thinking that I'm like, an anti-vaxxer or pro-vaxxer, I work with big pharma companies. I published in the major journals in the world. So it's not I'm coming out of some left field here. So I want to share some of that with you, and you also will get educated what's going on in biology right now. Biology is moving, or systems biology is bringing us very powerful tools where we're going to be able to solve diseases in a very different way if we want to, and we're going to be able to personalize it. So by the way, anyone heard of Alzheimer's and Parkinson's, all these diseases, right? There's a lot of research showing, by the way, this is, if you think about this as a piece of the brain, the astrocyte, this is the endothelium, this is called the pericytes, okay? When blood flows through your brain, you have the blood-brain barrier, toxins are removed, and things are nourished, and the blood-brain barrier decides what goes into the brain, what stays here. Anyway, there's been a growing recognition that most of these neurovascular diseases are the destruction of the pericytes, the structure, which means your blood-brain barrier is compromised, stuff comes in that shouldn't, and stuff that's supposed to be removed doesn't get removed. So what we've done with this kind of technology is we literally went through every piece of literature written, and we created the first molecular systems map of all neurovascular diseases. To keep it simply, we created what's called an engineering architecture. So if you look at this building, you have the foundation, you have the plumbing and the electricity, and then you have the interior design, right? Well, what we went through was, this is the foundation. So this is the endothelial, the pericytes, and the astrocytes. We mapped out all the molecular pathways. We found how they communicate, the communication layer. And then we took every disease. And by the way, none of this we're making up. We literally took all the literature and integrated. What you see here is Alzheimer's and, for example, ALS. They're both dysfunctions in a similar pathway. Pharmaceutical companies love to put everything as individual diseases, because then you can create a single solution for each one. But what this shows is that these diseases are literally various manifestations of different types of things that could occur, and that could occur because of different phenomena that's taking place. Anyway, when we submitted this, just to give you, oops, what happened? Can you, Prabhakar, can you just say okay to that? Sorry. And just let me go back, thanks. Yeah, just cancel that, Prabhakar. Yeah. Can you start back for me? Where was it? Sorry about that. Some of these fonts on these. Oh, there. So, there you go. So the reason I'm sharing this with you is when we Nature, Neuroscience, you know, all these big journals, they have impact factors like Academy Award ratings. Nature is considered one of the biggest journals in the world. And when we submitted this, half of the reviewers thought this was brilliant, and the other half said, what is this engineering system stuff? We don't know what you're talking about, this must be all BS. So we had to write back a 30-page response educating these neuroscientists on engineering approaches. Anyway, it got published in Nature Neuroscience. It's a big win. But it basically took biology to an engineering systems approach. Now, some people said, well, this is all interesting diagrams, but can you actually use these technologies to do large-scale complex modeling, right? So, how many people here exercise? A lot of people exercise here? Okay, well, when you exercise, this is your arteries, blood flows through your arteries, and the reason exercise is good, you get vasodilation, your body releases an important chemical called nitric oxide. All right, I think Time magazine said nitric oxide was the molecule of the century. When blood flows through here, there's a series of chemical interactions that takes place in the presence of arginine, and you get NO. Andrew Koo, one of my colleagues at MIT and Brigham, literally set up a wet lab experiment where he could send blood flow and he could measure nitric oxide release. Very painstaking to do. If you look on the surface, so if you see the surface, it looks like your bathroom tiles. These are the endothelial cells. And if you look on that surface, there's a structure called the glycocalyx. It's like a Christmas tree. It moves when blood flows, and when it moves through a series of chemical reactions, nitric oxide gets released. If you go look at the literature, it's like the blind man touching the elephant. Everyone has their view. You'll see these little ball and stick diagrams. There's thousands of them. So if you can integrate them, you can develop a mechanistic, not just some statistics, understanding of this phenomenon. And that's what we did. And what you're seeing here is this line here, the black line is the actual mathematical prediction. You know what these dots are? That's the actual wet lab results done in the lab. So it's not a curve fit. So what we're showing is that the mathematics can actually predict real phenomena. This was quite an important thing because up until then, the biologist said this is too complicated, you can't do this stuff. And this was published in one of the other big journals in the world called Cell Biophysical Journal. All right? So I'm sharing that with you to show that we're moving to a point where we can understand complex systems, we can model them, and this is where even pharmaceutical companies want to go because, you know why? It's taking them too long, they're losing a lot of money, just from the pure economic side. The other one I want to share with you is the power of this to actually start solving and looking at diseases in a new way. This was a paper that came out in Nature saying if you're going to solve cancer, you have to start doing combinations, cocktails of medicines. Why are they saying this? Well, if I gave you this much chemotherapy, this much dosage, it could also have toxicity. So people are saying, why don't I lower the dosage and combine lots of little things, cocktails? But some of you into the health world will say, duh, that's what food is, right? That's what, because food is multi-combination therapy. The interesting thing was, I don't know any of the authors, but Cytosol, the technology I created, was the only one cited in that paper as able to do combination therapy. So we went and said, why don't we do this? So we went literally, raised some money, and we modeled all the molecular pathways of pancreatic cancer, went through 10 million different combinations on the computer, found 70 that were viable, and we actually got one allowed by the FDA. So when we submitted this, the FDA contacted us. They said, we never really make outbound calls, but we were so impressed with what you were doing. This is where we want to move to the 23rd century. Again, I'm sharing that with you to let you know there are people in what you may call big pharma who also have kids, who also want to see their loved ones get better. It's not some monolithic unit, okay? So anyway, this got allowed, but it gave us credibility that we could work with the big guys. And in closing, where you want to, just to finish this, is how many people are into like eating well and know what turmeric is? Okay? Well, in India, it turns out, you know, curry, if you go eat curry powder, the curry is actually a mixture of herbs, combination, turmeric being the active ingredient in curry, and then curcumin being the active in turmeric. It turned out about 15 years ago, Indians get 1/3, it was found epidemiologically, Indians get 1/3 less liver cancer than their Asian counterparts in China. And people found that it was likely curcumin. And since then, there's been 6,000 papers published on curcumin. So what we did was, this is just to show you the power of this systems approach. This outer cell represents a cell wall, this outer circle. This represents the inner cell wall, the nucleus. And we literally mapped out all the chemical reactions from those papers. We're not saying it's perfect, but we put it all together where curcumin hits. So you can actually see curcumin inhibits various processes. Over on the far left over there, you can see curcumin hits a process that the same thing Advil does, ibuprofen. So it stops inflammation. So we were able to mathematically model this. Similarly, we did this for resveratrol. You know, if you're drinking wine, so imagine you're having now your Indian meal with some red wine. We're literally modeling what this occurs, and we could literally run mathematical experiments now. So the first row, the far left, right here, we're modeling inflammation. So to keep it simple, 0.15 means you have high inflammation in the body. I'm not giving any curcumin, any resveratrol. See that? You have high inflammation. Then I just give curcumin, it comes down. Everyone see that to 0.05? Then I just give resveratrol, oops, it comes down. And then finally I do a combination. You notice what I've done in the combination? I've reduced the amount of turmeric, I've reduced the amount of resveratrol, but you see what happens? It goes down even farther. This is called the synergistic effect. This is why food is powerful. This is why people want to do cocktails. Is that clear? But we're able to understand this versus someone just hand-waving, oh yeah, I put this stuff together, or at Whole Foods, why it works. So I give you that background because the journey that brought us here today comes from a journey of going through, starting in India, with my grandmother doing this stuff, to going to MIT, getting a bunch of degrees, and being able to do this. And we today work with the biggest pharma companies in the world. We work with nutraceutical companies who actually want to create products that work. The other part of Massachusetts here, it's a cradle of freedom, right? You have, you know, Paul Revere's run that took place here. You have Lexington, Bunker Hill. All of this stuff took place here. So the other aspect of my journey that brings us here is really a desire for freedom. Remember I told you about the email thing? Well, part of that thing I didn't tell you was when it went into the Smithsonian. The day it went into the Smithsonian, it created this huge uproar, okay? Because I didn't promote it for 35 years. People call me all sorts of names. You can see that here. Gawker Media. And you should read this because this is the kind of vile stuff that took place on the internet, which takes place in this discourse. Okay? This is not in 1940, Jackie Robinson. This is in 2012. The thought of a dark-skinned Indian guy inventing email in Newark bothers some people. Okay? And these were done by people who claim to be liberals, okay, in their meaning. So, and behind this was the media, who was supported by historians who had already concluded that email was done by the military. How dare this guy promote that he did the invention of email? Historian, and it was almost a new skull was found in Africa that had to be beaten out of history. And behind that guy was Raytheon, who's down the street, who had already written that they had invented email. Why? Because it was a $270 billion cybersecurity market, and they had branded themselves as the inventors of email. So when this stuff went in, it created a huge problem for them. They're branded. But what people didn't know is that I've been a fighter also. Several years ago when I went to India, I was recruited by the Prime Minister of India on my Fulbright to run the largest scientific institution within. About 6 months I found out they just wanted the MIT guy there. They didn't want to do anything. I exposed the corruption in India. I got fired. It was all over India news. Had to escape India up through Nepal. Then to come home. True story. Okay? The current Prime Minister invited me back, and that's my trip that I took home. Okay? And when I got home, Nature had me write an article on, hey, India has all these smart people. How come no Nobel Prize scientists have ever come indigenously from India? I don't know if you know that. You have to leave India. Gobind Khurana couldn't get a job as an instructor in India because of the corruption. He comes here, he ends up at MIT, and he ends up winning the Nobel Prize in Medicine. So India has a lot of smart people. It's quite corrupt. So I wrote this article called Innovation Demands Freedom, How Science Demands Freedom. All right? And this is a picture of me burning the South African flag when I was a 17-year-old kid on the steps of MIT, because MIT had investments in South Africa. That's me challenging the president of MIT. That's me fighting when one of my friends was thrown in jail by the Sri Lankan government. And that's me on my PhD graduation saying U.S. out of Iraq. So, and by the way, getting back to the invention of email, when all of this took place, this is a guy who was attacking me, and he was part of the military-industrial complex, and he had forgotten he had written that article in December 1977. The good news is, one of my mentors was Noam Chomsky, and Noam came out and he said, it's obvious who invented email. And at the same time, Walter Isaacson, who's this liberal guy who wrote the book on Steve Jobs, he writes this book right in the heat of this controversy about innovators of the digital revolution, okay? Email is left out of this historical book. And I just want you to look at this. These are the only innovators Isaacson could find. Okay, do you see a problem here? All right? So there's no darkies. There is. There's no people of color who invented anything. So, and he ends his book by talking about this guy. You know, he is Vannevar Bush, who was the president of MIT, who went and started Raytheon. And Isaacson argues that all great innovation comes from the military-industrial academic complex, the Golden Triangle. And by the way, I wasn't part of that. I was on the front page inventing many other things. But that picture doesn't fit well with that. Okay? And it's not a race thing alone, it's the fact that it was done in Newark. Now, I give this context because there's been a lot of very important things in science that the academic establishment has become the oldest profession now. And this is a great movie you should see called The Inside Job. It really is about, remember when the financial collapse took place in 2008? It's about what actually took place. This is a professor at Columbia. He had written this beautiful article saying the financial stability of Iceland. Okay? You know what happened, right? That article, lots of money went to Iceland because we thought it was a great economy, and then it collapsed. This guy in the movie, he shows that he changed his own resume on his Columbia website to say the instability of the, okay? This is modern academia. And we also know the story of smoking, right? For 50 years it was said that smoking was good for you. And there's a great book, Professor Chomsky told me to read it this time, called The Golden Holocaust, which brings this out. So, by the way, getting back to Gawker, I decided to sue them. And not only did I win a $750,000 settlement, but we also put them out of business, okay? And they had to remove those 3 articles. So the reason I shared the what my journey to Massachusetts, I think the amazing opportunity we have today is that this is a center of freedom, right? Truth and health. That's what we're at. Or we could become the center of power, profit, and control. And the vaccine discourse has the opportunity to really expose these dynamics. So that's the background. Let's go to what does it mean to be healthy, right? What does this really mean? Because my journey is that the real opportunity with health is resilience. What is resilience? That's what it really is, right? What does it mean to be healthy? So let's talk about resilience, and one way to think about it is use it or lose it. All right? Now, resilience, there's a whole history that people have talked about resilience, and it really comes down to stress and stillness. Your body, all these systems that we have biologically, we're not supposed to be just sitting still all day, right? Or you get flabby. We were supposed to stress these systems. Hans Selye was really the guy who really started defining stress. But stress actually comes from an engineering term. Stress is actually when you put stress, like if you take a building, you can have, what's called normal stress or shear stress. It's an actual engineering term. And when you stress things, like for example, if you stress an object like this, you have to be careful because if you stress it just right, it'll spring back. But if you stress it too much, it can break, right? So stress it's a very interesting modulator because you put enough stress, things actually get used, they get strong. If you don't stress things enough, you can actually weaken them. For example, if you own an apartment, I have one in New York, and if I don't use it, I have friends go there and actually flush the toilet and move things around. You want people to use stuff. The definition of stress, there's many definitions, but one of the key things is really the ability to face different trauma, the ability that when you get stressful situations, you're able to perform, and that's really strength. That's where strength comes from. So resilience is a very important concept. And the way, and in science and engineering, you can measure resilience by the spare capacity, by flexibility, by how you're able to rebound to situations. Some people are really strong. No matter what happens to their lives, they're able to come back. Some people look at people's lives who've undergone awful things when they were young, and they sometimes end up becoming the most successful people versus people where everything was given to them. And the neurobiology resilience is a big area of research, which is how do you create resilience. So the issue is not how you just simply be stress-free, knowing that we're all going to have stress. How do you create resilience? And there's been papers written on this, but one of the things that comes out of that is what they call stress inoculation. Interesting term. That you give yourself a certain amount of stress and you take it away. So when you exercise, we all know this, right? Typically if you do weightlifting, people say you should do a 2 days on, 1 day off, 2 days on, 2 days off, right? Why? Because if you exercise too much, you're going to start breaking down muscle tissue. On the other hand, if you simply sit around, things go flabby. And what they found is that there are neurotransmitters in your body that get resilient to these stress inoculations. And so if this is your normal mode of stress, they're finding that with stress inoculation, you get performance improvement in multiple ways. You can do better performance under less stress. But anyway, the bottom line is stress is not a bad thing, and you have to learn how to use it in important ways. The Japanese swords, I don't know if you know how they're made. They put massive amount of heat, they then, cool them. Massive amount of heat, cool them. You're doing both. In yoga, how many people practice yoga? If you do most yoga forms, you're supposed to be, you do standing postures and you do Shavasana, right? You go back and forth. There's a reason for this because you want the nervous system to chill out, and then you want exercises. Is this making sense? So the notion of resilience is, I think, where we really want to point to. That's what this is all about. All the systems in our body were designed to be resilient. How do you, now, resilience is cool, but each one of us is very different, right? If you have someone who's suddenly had a major injury, you can't tell them, well, go start exercising back right away. They need to go through a different stress inoculation, right, to get back to strength, back to where they were. Someone else has already been working out regularly, they can go to a different level. So this is very, very personalized, which means one size does not fit all. Okay? So we want to get resilient, one size doesn't fit all, and this is why the big growth right now, opportunity, is personalized medicine. At the last nutritional conference I went to, they said the number one, there are 3 trends that they saw taking place in healthcare. One is millennials want authenticity. Number 2 is pet, believe it or not, pets. If you want to start companies in there, pet care. The third was personalization. People don't want, one size fits all. They want personalized medicine. Around 2003 to 2006 is when all the work in systems biology was taking place. That's when the NIH director, Francis Collins, even Obama started using this term, precision medicine. But it's about recognizing we need to go personal with medicine. And a simple way of thinking that is the right medicine or the right treatment for the right person at the right time. And all of this is really about, in my view, resilience. It's about you want to build personal resilience for yourself, and so you make choices. You go to a personal trainer, right? You go to your personal yoga teacher. They should technically not be giving you all the same yoga postures. You go to your doctor, who should be having a patient-doctor relationship with you, and out of that very personal relationship for you or your child or your family is where health emerges. It's not one size fits all. So the key part of personalization is when you're implementing methods to affect these systems, two variables are important: safety and efficacy. Okay? You don't want to do certain things that can harm you, nor do you want to do things that are non-efficacious. So for example, if you want to build your body and you want to put on a lot of muscle, well, one way is you go through a certain process. Well, the other way is you can take a steroid, right? That may have a certain effect, but it could also shrink other things, okay? But so you have that, you have some efficacy for a short term, but you have other things that it affects. Dr. Deonikar is going to talk to you about this when we look at genetically engineered food, some of the work we've done there. So in order to achieve safety and efficacy, we have to take a systems approach. Okay, so let me repeat again. We want resilience. Everyone agree with that? In order to get resilience, each one of us is very different. We need personalization, which means the right treatment or the right medicine for the right person at the right time. But in order to do personalization, we need to be safe and efficacious, right? But safety and efficacy come from a systems approach versus the reductionist approach. And just to give you a fun example here, some of the work we've done is the integration of Eastern and Western medicine. There's a tool we have called Your Body, Your System. And you can actually answer a series of questions. And in this triangle, it'll figure out your body type. It's an integration of the Eastern system with modern systems theory. I don't have a chance to go through that, but that red dot represents you. And then you can take another series of questions, and the black dot represents how you deviated from your own homeostasis. In the Indian system, they call this your bikrithi. We call it your disturbance. And then you can take the system will recommend to you particular foods or particular things you should take for you that will help you get back into balance. And this is really the notion of health. Each one of us has a particular way we operate well. You deviate from that by, I don't know, jet lag, this, flying around, but not eating right. And the goal is to get back to who you are, right? So the way we get there is through a whole systems approach. So now I want to go to the immune system with that background. We've talked about resilience. We've talked about precision medicine. We've talked about the fact that we have tools now. So let's talk about the immune system. Do we want to take a whole systems approach to understand the immune system, or are we currently taking a reductionist approach? Which means, are we looking at, how are we actually looking at whether the immune system is functioning well? How do we know anyone in this room right now who's got a very strong, resilient immune system? What are the variables of that? Is it simply the measure of the number of white blood cells? And if you have this antibody or that? Because that is currently the current model of measuring the immune system. Do you guys know that? The 1915 model is white blood cell count. The 1959 model, right, Prabhakar, is whole blood count. And then we added antibodies. These three variables, or these two variables, are all we use to measure if your immune system is stronger than your immune system. Okay? So think about that for a second. We're using a single variable called, oh, I exposed you to something, you got this antibody, and therefore you have a strong immune system. Does that sound right? Because these are very complex systems, and we're going to get into this. So that's called reductionism. So when we talk about vaccines, by the way, vaccines are not, the concept of immunity is the key. Resilience, right? Getting your body, in China, for example, and even in India, they had a process called variolation. Everyone heard of this? They would literally take someone, if they had smallpox, take the entire pus and shoot it up someone's nose, okay? And the idea was to expose them to it. So this is not... Yeah, I know, it's gross. And by the way, an African slave is the one who brought this technique here when we started inoculating the troops in the United States. Washington knew the British could be spreading smallpox, so we got 40,000 of his troops through this technique. It wasn't, it was literally they would make a little incision and they would give the entire virus, okay? The whole thing, whole system. And some would argue that helped win the war. And then Edward Jenner started doing that with cowpox. So what are we trying to do here? If the goal is to create immunity, let's all agree that's a good thing. So one way you could create immunity is you play in dirt, you expose yourself to all sorts of exogenous stuff, and then your body creates immunity. So we're going to take this slow, but you're going to really get a systems perspective on immunity and what I believe is a real flaw in this entire discourse that's taking place. So some of you may know we have an innate immune system and an adaptive immune system. How many people know about this? Okay, so the innate immune system is the thing that is your skin. It's called your mucous membranes. People are calling it part of your microbiome now. It's what the pathogens first connect with, and they have a methodology of reacting to that, okay? Which is called the early immune system, which responds to that and interacts with that. The typical theory was this system has no memory. This system is basically all or nothing. It just goes after everything. It's a bunch of soldiers who just start shooting at everything. And the adaptive immune system is a system that then kicks in after that to be very specific. So if you got someone sneezed on you and they had measles or something, right? A bunch of different chemical forces go to attack that. Within the first 72 hours of exposure, you get fever, rash, etc. And then after that, your body, the adaptive immune system, creates what they call an antibody against that particular virus. This is sort of the standard model of immunology, right? So, and by the way, to give you an idea, the innate immune system has physical, it's got the skin, the cough, the tears, and mucosal layer. It's got monocyte, macrophages, neutrophils. You don't need to know this, but the point is the innate immune system has different arsenal than what they call the adaptive immune system, which is T cells, B cells, etc. Right? Is that clear? So you got these two systems. One is what you're exposed to, the other is. Now, and by the way, there's some interesting differences between these systems. Typically you would learn is that how fast these occur. The innate immune system is pretty quick. It's either on or off. Its potency is lower. The kinetics, it's a few days. So if you get exposed to something, if you notice if you get a flu or something, right? The first 3-4 days are the most horrible, right? Because your body's trying to protect itself through the innate immune system. All right? The adaptive immune system has different characteristics. It's a little bit longer, it's very specific, etc. What I want to now walk you through is a different way of looking at this. So this is how we in engineering systems look at the world, okay? So you have the innate immune system, you have the adaptive immune system, and then some antibodies typically created. We got there? Yeah. And a pathogen comes here. This is what people typically see this as. Is that clear? This is what's known. And a vaccine really doesn't go through here, it goes to the adaptive immune system. Okay? See a problem with that? Okay. But it gets even more interesting, because this is what's been really left out of the discourse. What really is going on is you have the innate immune system, but there is a missing link system that's rarely talked about in this discourse. It's called the interferon system. The IFN system. And we're going to talk about this because by understanding this, you're going to arm yourself with some very valuable information that's really going to help hopefully unite this unfortunate division. There's the IFN system. It's called the interferon system. The interferon system was discovered by Lindemann and Sachs, right? And the interferon system is really the missing link between the innate immune system and the adaptive immune system. And it turns out when you actually look at this, it's not just one model like this, there's actually feedback. When you get hit with the pathogen, the innate immune system turns on. The IFN system then gets kicked in, which then initiates your adaptive immune system, and then the adaptive immune system closes a loop to clean up stuff. All right? This is the latest stuff that's coming on. This model is a model of the 1950s. It's really old, probably in the 1915s. But this is a model that we're still using today. And you can, But the good news is people want to move to this. Now, when I did my work at MIT, I did a lot of focus on this, and it was just fortuitous when I got involved in this effort here, is I went back and looked at the work I'd done, and I'm going to share that with you because, you know, first of all, you can't get a degree out of MIT, particularly your PhD, unless you actually do something new. And when you present your PhD thesis, the entire faculty is invited. It's a huge defense you have to do. So to anyone questioning my background in this field, we can have a discussion about it. Let me talk to you about the interferon system, okay? It turns out that recent research shows that when you get a virus, remember the old model was the adaptive, the innate system just turns on and is on or off? The latest research in Japan shows, I think this just came out in 2018, just 1 year ago. So the old model was the innate immune system, when stuff comes through, it's a dumb system, it doesn't know anything. It turns out, when you get a viral infection through your innate immune system, that the system actually turns on, in the next case, the genes actually get remolded up to 1,000 genes. And the next time you get hit with that virus, those 1,000 genes are ready. There's memory in the innate immune system. Okay? This is very important because what this means is that there's a whole bunch of genetic molecular systems taking place. It's not just all or nothing, which was the old model. That when you get hit with a virus coming in through this way, or pathogens, genes are actually getting remodeled, which means it's called epigenetics. Genes that were not turned on the first time the virus hit, the next time they get turned on, if we can talk more if you want to detail, it's called the histone groups, which control the DNA, actually get remolded, so those genes can get turned on. Very, very fascinating research, which means the innate immune system is not just a dumb system, which is what we've been all told to do, that the adaptive immune system is smart and the innate immune system is dumb, so it's no big deal short-circuiting that. The other interesting thing is there are different kinds of interferons. I'm going to talk about the interferon system. The interferon system is a linkage between the innate and the adaptive. Interferons were discovered in the 50s when we noticed that when something got infected with a virus, that the next time another virus came, the thing was resilient to it. So let me repeat that. A virus infection takes place, but in the local area of that virus, when another virus came, that thing protected itself from other viruses. This was called viral interference. Viral interference. And again, what's fascinating is this does not get brought up in this discussion about vaccines. That when you get exposed to one pathogen, your body actually gets ready for fighting many other pathogens. Okay? And it's doing that through interferons. There's type 1 and type 2 interferons, and these interferons are activated initially by the innate immune system, but they themselves have their own cascade of systems. Type 2 interferons stimulate the anti-inflammatory response, are involved in the linkage to the adaptive immune system. The key thing I want you to take away, you have the innate immune system that I'm sharing with you. New, very fascinating research is showing that there's memory. The interferon system is a bridge, and I'm going to walk you through this. Okay, I'm going to walk you through this diagram. Andres, I'm going to go over here if it's okay. I'm going to walk you through this, but I want you to understand this diagram for two reasons. First reason is it's going to look really complicated, but you're going to get it. But by the way, do you see, this is just one subsystem within a very complex system. This is some of the great work done by Taniguchi. And what we did was I literally took this entire system, the interferon system, and we used our technology to model it, which matches what's going on. But what I'm going to walk you through is, it's going to seem, so if you can follow me, you're going to learn a lot in the next 5 minutes, okay? This outer circle, everyone know what a cell is, right? Outer circle is where all the DNA is. Outer circle is the cell membrane. Everyone got that? Yes?
Yeah, that's...
Okay, good. So this is the outer, by the way, we're looking at one cell. This is the outer circle here, and this is the inner circle here, which is where all the DNA material is. All right? You see what it says here? Virus. So when a virus lands, I've done a great animation, which I actually modeled. I don't have it here, but I think you can understand it. So a virus lands, right? Someone sneezes on you, and a virus lands on one of your cells. Okay? Watch what happens. When that virus lands, the first phase, remember I told you when you first get infected, you get a little rash and a fever. This all occurs within 72 hours, what I'm going to walk you through. When that virus lands on your body, a series of chemical reactions go. Just look at the step one. And within your body, they're called interferon regulatory factors. They're just hanging out there for that virus. So think about that. Just think about that. Your body has chemicals waiting for these enemies that we've called enemies. So when IRF3 interacts with that virus, this gets translated to your genome, and your body creates IFN beta. It's called interferon beta. Some people have tried to create medicines from interferon beta. So your body, first of all, creates interferon beta. Everyone got it? So virus lands, your body has some interesting chemicals which know how to react with that virus. It gets translated to your genome, and your DNA translates and transcribes IFN beta. Step one. This IFN beta can either, you see it goes over here, this can be another cell. So one cell gets infected, right now I'm showing it on the same cell, it can go to another cell, and it basically say, hey Bob, I've been infected, okay? So it's a signaling. It's called a cytokine. So IFN beta goes, and so now assume this is a different cell, and lands on a receptor and says, hey Bob, or says Bob got infected. When this lands on this cell, the second phase occurs. A series of chemical reactions goes, and then the body actually creates these things called IRF7. Okay? So your body, cell 1 got infected by a virus. It too may create, it communicates to itself or to another cell, and the body creates another chemical called IRF7. And that's just hanging out, waiting. The next time a virus comes, could be a completely different virus. Guess what your body does? It interacts, the IRF7 interacts with that virus, and it unleashes a nuclear arsenal of IFN beta and alpha, which are very powerful things that arrest that virus. Let me walk through this again. Virus comes, the body is smart enough to create IFN beta, which signals another cell and tells it to get ready by creating these chemicals. This virus comes and it releases a nuclear arsenal. What does that tell you? That tells you these pathogens are good for us. That the body is waiting for these things so it can develop viral interference through these IRF7s. Any? Yeah?
Actually, I can hold the mic more.
What's the matter? You can't hear?
Just
I'll just stay here then. So what I'm trying to share here is that you have a phenomenon of when you step back and look at this, who the hell ever said a virus is bad? Why would the body have all this? This is within the interferon system. We're not even talking about the adaptive. So this clearly shows that mechanistically the body has the ability to create and signal and get ready for the second virus to come. Does that make sense? Okay, here, this one, stay here. Does that make sense? It's cool, right? The body has wisdom, it has mechanisms. Can I say, yeah. It has the ability, and it wants these pathogens. That's what I take away from this. Because without creating these, you would get assaulted by viruses. You would need thousands of vaccines. That's where this are, tens of thousands. So this tells me, so the viral interference phenomenon is not talked about in this discourse. And by the way, so when we did this, my work at MIT was literally understanding all of this, and I went and modeled all these four mechanisms. The first phase is called receptor signaling. The second phase is called the virus infection, the receptor signaling, and the amplification cycle, which is this. By the way, this is what's really cool. There's a fourth phase where your body, it's a little bit hard to see, actually goes and turns this off. If it simply kept doing it, your body would be an autoimmune disorder all day long, right? So the body also knows how to turn these things off and modulate this process. So there's the viral infection, there's the receptor signaling, there's the amplification, and there's the cycle to stop it. So with our technology, we literally took all these pathways, which we found in all the literature, thousands of pieces of literature, and then we were actually able to model it. What you're seeing here, see this pink line? That's IFN beta, which is that first virus infected. That comes, and then right slightly after that comes IFN alpha. And you can see the time course on this, and this is within about 8 hours, okay? And guess what? This matches what people have seen literally over a 24-hour period. Our data matches what people have actually seen in clinical work. So we're actually able to understand mechanistically this phenomenon. It's cool, isn't it? So what I'm trying to share with you is that when you look at this entire system, and the way to look at it is, do vaccines bypass and short-circuit that system? Okay? Does upregulation, for example, of a protein like HBGM1, which is shown in neuroinflammation, how does that affect things? And do we know the risk of bypassing the IFN system? And is there a risk matrix for vaccines? So by the way, when you look at the immune system, it's involved in everything, guys. This is, by the way, a recent paper that came out. I'll give you the reference after we come back. It's a new paper. Just a year ago, people are saying now we need to do systems immunology. Okay? About time. But look at how many things the immune system's involved in. You screw with this, you can affect a lot of stuff. And what this paper ends, this is a paper that just came out at the end of 2017. It says, and this is written by I think Howard Hughes Medical, and these are not, it says, a case in point is that the main immunological metrics used widely in medicine are white blood cell counts and the complete blood cell count. The former was developed in 1915 and the latter was developed in 1959. It's time for an upgrade. Okay? Fantastic paper. So I'm saying this because, well, we've already understood this, but it's good when other colleagues also say this and put this out there. But this is probably one of the most important points. And this is science now. It's system science. It's not saying I gave one thing and I see something else. Now, so here's really the big question. So the summary of this discussion is the following. Is you get a pathogen, it can go through this way, right? We can go this way, which is exposure. We hit the innate, we hit the IFN, we hit the adaptive, and you get immune response. Now, what are the risks of this, and what are the benefits of this? Good question, right? Or we go right to the adaptive. And what are the risks of this, and what are the benefits of this? Does this make sense? Have you ever seen it like this? This is the takeaway diagram. Like, you can do this, you can do this. Where is the risk matrix? Because now we're talking engineering. If you're going to go short circuit, we have I don't know where Frank is, but if Frank's going to go do re-electrical work here and say, we just had some wiring work done on our data center. The first thing I say is, what's the risk of if we short circuit the generator and we do this? What's going to be the problems? Right? But this is what we're talking about. Now, have we figured all of the details out? No way. But this is what needs to be figured out. But we are definitely doing this. And we're not saying don't do this either, but if you're going to do this, it has to be personalized. Because some people may have they've never been exposed to anything. They lived in a nice little bubble all day, right? Maybe you need to titer some vaccines to them in some fashion we don't know yet, instead of just throwing them into a slum. Some people have grown up in slums. And this explains why, if you go back to resilience, when we started doing, clean water, when we started adding, sewage treatment, when we started adding vitamin A, you saw a huge decline because the resilience model was at the other extreme. People were being exposed to so much pathogens that their system was constantly being hit, right? And if you don't get exposed to enough things, you don't build resilience. So you can have extreme stressors all the time, or you can have no stressors. There is a middle path, and that middle path is a personal thing that needs to be figured out for each person. By the way, this is an interesting, there's a chart, I don't know if you've seen in the inserts. We'll send it out, but is Aaron here? Siri? Did he show up? Oh, there's Aaron. Aaron shared with me a great Excel spreadsheet, which basically is an awesome spreadsheet that he put together, which basically has, for every vaccine, the potential risks of disease that may cause. It's actually in the inserts, right, Aaron?
It's just a summary of each of the post-licensure adverse events and diseases that each manufacturer discloses in the package.
In the vaccine.
For each vaccine.
Right, so the real issue is if you have the immune system, we know that certain vaccines may, the blue lines mean that it's causing that disease, and then here you have the normal exposure. This may actually inhibit some of those diseases. It turns out interferons, and by the way, I have a paper coming out that will be up online that summarizes all this in a much more scientific format, which we'll be putting out. We wanted to have it ready, but it'll be coming out within the week. You can go get it, you can pre-order it, it's up there. But it actually shows that many of these interferons actually inhibit many of the autoimmune diseases. Okay? So we've been talking about adjuvants, but I'm taking it even one more level deeper, that these pathogens may initiate interferons which actually protect us from many of these autoimmune disorders. Is this making sense? Okay? The interferon system, viral interference, the innate immune system, subverting that, short-circuiting that, could have many other things. And we've only, the work we've done with interferons to start showing that. So if you look at, by the way, this is not our work, but there's a lot of data showing that when you get infected by measles, right, there's many diseases that it actually averts. There's, for example, this lowers risk of lymph cancer, right? A natural cancer measles infection lowers, what is that, breast? Yeah, breast cancer. Natural measles infection lowers prostate cancer. So, and this adds up because you're building viral interference. Interferons are good for stopping other diseases. So, let's wrap up here. The Declaration of Independence really says we all need to have life, liberty, and the pursuit of happiness, right? And the march of humanity has been through this process where we've gone from slavery to becoming serfs and wage slaves, but it's been a long process of freedom. And in this discussion, when we look at, it's always been what I want and what the collective wants. And I've talked about this before. It's an interesting balance, right? I want to do whatever the hell I want to pursue my dreams, but then I live in a collective, and how do you balance this? And this is really this concept of risk versus benefit. And in this process, what we do in other fields of engineering is we do these risk matrices. And we'll come back to this in the final session, but for any choice you make in life, I'm going to take a vaccine, I'm not going to take a vaccine. I'm going to drive a car, I'm not going to drive a car. Those decisions, you decide what is the occurrence of an accident occurring, harm occurring, and if that occurs, how catastrophic will it be? And those two probabilities help you design this, and we'll come back to this. Now, what would be ideal is, should I take the measles vaccines or not take it? Okay? And for my personal situation, can you show me a risk matrix? Because if I take the measles vaccine, there's some indication that neuroinflammation may occur, which is catastrophic. And what is the, relative to not taking the vaccine, right? What is the relative risk? Some data shows 1 out of 100,000, or 1 out of a million, or I think 1 out of 100,000 if you want, or 1 out of 1,700, 0.001% of you getting neuroinflammation by not taking the vaccine. And about 1 out of 88 when you do take the vaccine. So it's 1.136% versus 0.001%. So now, if we need to have these risk matrices. They don't exist in this field. And by the way, there's ways to do this. People calculate probabilities. By the way, in the area of risk, some people may have, risks that are not real also, okay? But in the area of auto insurance, for example, we make it very personalized, right? If you're an 18-year-old and you have 20 DUIs, you're probably higher risk than someone who's 15 who's never had an accident. And we create insurance programs out of that. And in closing, what I want to say is that this entire field is an engineering problem. MIT created the Department of Biological Engineering. They went away, biologists do their stuff. Why did they create the Department of Biological Engineering? You know why? Because vaccines are a product of engineering. Pharmaceutical products are a product of engineering. Biomedical devices are a product of engineering. And in engineering, you're always focused on risk. And in engineering, the other big thing is you do not treat the customer like dirt, okay? Let me explain. If I build a bridge, or I build an airplane, and I could have flown these airplanes a million times, and one airplane falls out of the sky, and someone says, you know, the airplane fell out. You don't go, well, that was 1 out of a million, shut the hell up, right? Or if you use a piece of software, and you call Apple, they don't say, well, everyone else is having fun, something must be wrong. You get pretty upset, right? In engineering, every customer matters. Because if one customer has a problem, it gives you an opportunity to understand a mechanism why something's wrong. And what I've come to conclude is that in engineering, when I build something, I take ownership for what I'm building. In medicine and in biology, we don't know how nature engineered these things. We don't know all the parts. We're only starting to understand them. However, the MD and the pediatrician, in their training, they're not trained to appreciate this engineering. In fact, unfortunately, it's not no blame to them. They've built a hubris to think that they already should know it all, and they don't know it all. In many ways, the MD and the pediatrician is at the end of a cycle. They're like the pilot who's flying the airplane, or tech support. I don't want to demean anyone, but they're at the end of a process. And they don't know about the entire engineering framework. And I think if we start looking at it this way, they haven't had a chance to consider all of these systems, right, that we just went through. They don't look at it this way. They're only starting to. So I think the opportunity, I'm going to end on this, I'm going to do some of the risk assessment when I come back to Debbie, but I think the important aspect here is that we're looking at the need for risk matrices, we're looking at the need for risk assessment models, we need to take an engineering systems approach. And that engineering systems approach needs to move this discourse to the notion of risk and understanding risk in this model. I'm going to end there, but I hope this helps. Any questions? Yeah. Well, no, Prabhakar, you can come on up. While Prabhakar's setting up, we're going to come back to this because I have some slides in the interest of time. How are we doing on time? Okay. All right. How are you guys doing? Do you mind if we go a little bit over? Okay. But, yes, Allison?
So I was listening to the some of the ACIP, which is the Immunization Advisory Committee on Immunization Protocols, and they many times said we don't have the data, we lack of data, we have no safety data or little safety data. Is this going to come along fast enough for us to use in this method? Because they're pushing through medications without any data, without any science, under assumptions that are already in place. How do we get this out there quicker with, do you need, extra, minds, people, what can we do?
Yeah, so Allison, so I have this paper that I'm putting together, this whole concept of that diagram, and that the immune system model that we're using is basically we're using like something that's 50 years old. And show that scientifically. That paper is coming out in less than a few days. That document, I think, could be very valuable because it basically says the science is not settled, and it also says that the immune system is far more complex, and it also shares the fact that we're missing this entire risk matrix. And I don't know if you can affect. I think the main thing to do is to bring out the fact that what they're basing this on is an old model. And I can give you a list of literature now, systems immunology, what they call systems vaccinology. These are just in the last 2 to 3 years. that are showing, just like that quote I just read you, like what they're doing is 100 years old. So I think for lawmakers, I don't want to say it's fake science, but it's really old science. And that science has moved forward in a very different way. And if you look at even the basics of this today, that the concept of the innate and the adaptive immune system, those models are freaking wrong. Period. Because you're not taking into effect all this. So in the paper I'm putting out, I'm saying, imagine you take a vaccinated and unvaccinated person. You should just be measuring antibodies. What about all these other interferons? There could be a whole bunch of other biomarkers the unvaccinated person has that could actually be a measure of resilience versus a vaccinated person doesn't have. And if that format is correct, that means every vaccine you're getting may be helping in some cases, but it could be lowering the level of other systems that get turned on. So we're basically going to become addicted to vaccines. So I think there's a way to present this, which basically says the science that we have today is 100 years behind. And the people promoting the science are MDs and people who are way at the bottom line of the process. In the risk assessment piece, we're going to talk about more of that. Does that help, Allison?
Yeah.
Okay.
I
So
have one other question.
yeah,
over
let's just
here.
take one more. So listen, our thing was to go straight through because of the thing. Should we just keep going straight through?
Yes.
Okay, go ahead. One other question?
You want to just say what the question Yeah.
I wrote everything down on my card, but in the case of autoimmunity, as far as the B cells are concerned, for example, like lupus, I believe that someone who has lupus creates too many B cells. Is that the same as the INFB?
Yeah, well, no, it's different. So B cells are, this is IFN beta, it's different. It's something, interferons are a different class of chemicals than what the B cells and those things are doing. Okay?
So they're not the same?
Well, they could be created by B cells, okay? But I'm saying they're created by plasmodendritic cells, right?
They can regulate the downstream adaptive.
Right, they can affect those things. I think the key takeaway is when people get lupus and these diseases, there's something perturbed. There's a systems perturbation that's taking place. And that systems perturbation can occur if you did, all these are regulatory systems. When you get lupus, it's essentially autoimmune disorder, right? Things are thinking they're always being under attack. And these systems are very finely tuned control systems. So if you go start perturbing something in one area that you think you've solved something, you actually may have put the system into an autoimmune mode. I mean, that it's always thinking it's fighting something.
Thank you.
Okay, let's go to Dr.
Thank
Deonikar.
you, Dr. Shiva.
Thank you.
Thank you. So after Dr. Prabhakar speaks, we'll come by and collect cards. Just if you're writing down questions, so we can try to get them answered. We'll now move to Dr. Deonikar, who holds a PhD in chemical engineering. He is a systems biologist. Dr. Prabhakar is originally from Bombay, India, and he now lives in Michigan. And we are very pleased and thankful for you joining us today, taking time to come to Cambridge, as so many of you have. And you're going to present and facilitate the session on vaccine and bioinformatics framework. Welcome, Dr. Prabhakar.
Thank you, Michelle, and good afternoon, everybody. It's going to be a tough act to follow, but I'll try my best. So, as a continuation of what Dr. Shiva had just gone over, in terms of the tools that we have to try to solve, and how we have been using that tool to analyze complex problems in a systems manner. So I'm going to go over the agenda first. That includes going over the existing tools and how they are, what their problems are, and what opportunities are there for us to overcome those problems. And I'm going to take two case studies where I will go through how we have used some of these tools that Shiva mentioned to analyze some of the hot button topics like GMO safety and a complex disease like osteoarthritis. And hopefully that will give us some idea of what lies in the future in terms of how we can use these tools to understand and answer the complex questions about vaccine safety assessment. And I'm also going to be moderating the working group interactions and the observer question session. So let me start with the first topic of the agenda. Science has been making a lot of progress over the last 30-40 years. The amount of scientific studies or papers that have come out is unparalleled to what has been done in the last maybe several hundred years. So what that has created is a very interesting problem of too much data. And that kind of, the issue with that is that it can lead to cherry picking of the data. It is impossible to analyze it at one shot, so you're going to miss something. So, but these are the problems that can be overcome. So, the way to overcome these problems is to create the tools, and that's where the new fields of bioinformatics and computational systems biology come into the picture. They help us to look at this huge amount of data and understand it from a systems point of view, understand the gaps in the existing system, and also expose the cherry picking and resolve conflicts like the vaccine issue or the GMO issue and so on. So just an example here, this is the public database that the government NIH maintains called PubMed. If you type in vaccines, you will come up with over one and a quarter million papers. So how are we actually supposed to go through all this literature and inform ourselves? So that's where people have been coming up with some tools to avoid the problems that I mentioned, cherry picking and the near impossible thing about manually trying to organize these. So some of the tools that have been developed are listed in here, but most of these tools have still some problems because they are kind of difficult to use. They are only for academic purposes, and the public is not able to understand them because it's a little bit dense side. So the opportunity here is to gather that information and put it together in a way that we can interconnect that information. So we have a systems view of it. That means we're not just looking at a part, but we're looking at the importance of that part for the whole entire system. And then we can reduce the reductionism and look at it from a systems view to advanced science. So one of the first case studies of how we have used the tool that Shiva developed during his PhD. Cytosol is this hard-button issue of GMOs. This is an article that Shiva read in 2014, and it piqued his interest so as to start this really novel project to look into the whole GMO debate using a scientific and systems-based approach. There have been many points. Some of them were pro-GMO, some of them were anti-GMO, and then but there was no kind of middle ground or a very unbiased approach. That's what we wanted to provide this debate using the systems bioinformatics tools and computational systems biology tools, because that is the only way you're going to parse through the large amount of science that exists. So towards that, and again, I mean, as you can imagine, there was no consensus between what is the difference between GMO and non-GMO, and they kind of look the same. Some of them taste the same. So when you're trying to define what is the difference, we go back to 1976, and when they started calling the GMOs as the same as that of the non-GMO equivalent, they point out this particular law of substantial equivalence. That means, and the origins of this law lie in the medical device industry, and they just applied it to food industry. So the issue there was that if you have developed a medical device like a stethoscope, it takes a certain amount of time, like 7 years, to get it approved by the FDA. But then if you change a very minor thing in that device, for example, a color, then to avoid the cycle of 7-year-old development or approval process, they came up with this law called substantial equivalence, where they say that if most of these features are same, the functionality is the same, then you can actually, for the sake of approval, consider it as an equivalent of the original device. So they very shrewdly applied the same principles to GMO versus non-GMO debate, and they did it so that they can avoid going through that rigorous approval process of making sure that the food product that they had come up with is actually safe for human consumption. So, even with this substantial equivalence, even though FDA is involved, all they do is rubber stamp it. They don't really actually go into the details of it. The manufacturer or the producer of that GMO variant has to just give an affidavit saying that we have done these tests, and then submit to FDA, and then FDA allows them to go forward in the market. So it's just to read this code, equivalence depends on the characteristics or the criteria selected, and not anything based on the new science. So we chose to look at genetic modifications in soybean because almost 97% of soybean that is produced in the States is genetically modified. And we chose to focus on a particular molecular system called C1 metabolism, which is involved across several organisms, plants included. So this is the mechanism that creates some of the essential amino acids within those organisms. So if you go on PubMed and type there the C1 metabolism, you will find almost 18,000 papers. So how do we characterize and kind of make sense of all this large amount of information? So we use the side-solve process where we gather all that information. So, there are about 17,000 papers, about 6,500 experiments that we reviewed using the bioinformatics approach across 23 countries and then 84 labs. And we mined that data to extract the mechanistic information. So what is the molecular processes that are involved in this particular metabolism? And that's a very critical metabolism. If something goes wrong with it, then the plant's host immune defense system kind of goes down. And you end up with a plant that has a weak immune system. It either dies or it produces inferior quality. And this is the mechanism that where people had introduced genetic modification so that they can use a particular pesticide which will kill the other weeds but not the plant. So the next step in this was to develop mathematical models using side-solve, and then we published a series of 4 papers to show the difference between the GMO and non-GMO variants at the molecular level. And what we found was that there was indeed some difference, which should have been taken into consideration while the approval process was going on. So again, these are the details of what we looked at. So it's a pretty exhaustive process. So we identified 3 molecular systems within the C1 metabolism: the methionine biosynthesis, the methylation cycle, and the formaldehyde have been observed. So this is also one of the key area which we focused, because there were some reports out of the farmers that some of their product was having the seeds, especially were accumulating formaldehyde, and it was showing up in the because basically corn and soy is fed to animals, so it was showing up in the animals that people eat, as well as there's some anecdotal as well as some studies show that the pesticide levels were also showing up in breast milk. So we wanted to focus on, that's why we wanted to focus on the C1 metabolism. So once we identify these mechanisms, so these are the molecules or the biochemical reactions that are involved in each of these three mechanisms, and then we mathematically model them, and we publish the first paper was just to review what's there in the existing literature, to identify what are the key mechanisms that are involved in that formaldehyde detoxification, and give a systems view to this whole issue of C1 metabolism, which is a focus of genetic modification. In the next study, we actually mathematically model these, and using cytosol, so we created individual models and then combined them using the cytosol platform. And what we found was that for the normal plant that is not genetically modified, this particular biomarker, the glutathione, it is a potent antioxidant, and it helps with the immune defense. It maintained at its steady state, so there was no degradation. The plant was producing it and consuming it at the same time producing it, so the levels of glutathione were constant. And we also looked at the formaldehyde concentrations in the plant. So there was formaldehyde produced because it is a byproduct of that detoxification process, but it was getting degraded, so there was no accumulation. So under the normal conditions, that is no genetic modification, you have a steady level of antioxidants, and then you have detoxification of a major formaldehyde is a carcinogen. So there is a detoxification happening. So and we varied the situations of the experiments, in situ experiments, and we still found the same results as you can see here, and that was also published. In the third paper, we went one step further, and we, because no mechanism exists in isolation, there are other biochemical, biological processes that it interacts with. So, for example, oxidative stress. So this is a very critical biological process. You need that to maintain a healthy lifestyle, but if it goes, it gets upregulated, then you get diseases from cardiovascular disease to cancer and so on. So, particularly in plants, the C1 metabolism is interacting with oxidative stress, and in a short while we'll know why this is important as well in the context of GMOs. So we chose to look at the interactions between the oxidative stress and the C1 metabolism for this particular study. So in the oxidative stress, there are, again, we have a tremendous amount of literature. We parse it through to identify the key molecular mechanisms that included the production of the reactive oxygen species, the lipid peroxidation that is caused by these oxidation species, and the ascorbate glutathione pathway. So this is where the glutathione also comes into the picture because it is an antioxidant. So how body maintains a healthy level of oxidative stress is captured in these three molecular mechanisms. So we were able to model these individually, and then we were able to also identify how the oxidative stress is affecting the C1 metabolism. So there are 2 points of interaction here. So the ascorbate glutathione pathway is affecting the methionine biosynthesis, which is the production of the amino acid, and at the same time, the ascorbate glutathione pathway is also affecting the formaldehyde detoxification, because glutathione is one of the key components of the detoxification pathways. Next, we mathematically model these together with, using the computational biology tool, cytosol, and we have the results here. So there are 2 conditions that we simulated, so 2 types of experiments we did here. One is with oxidative stress, the red line, and one is without oxidative stress. So if you remember from our first, second paper, the glutathione was being maintained by the plant at a constant level when there is no perturbation, no genetic modification, or no stress. But when you introduce oxidative stress, what happens is that there is a depletion in the levels of glutathione. So in the next slide, I have the formaldehyde results. So if you have no oxidative stress, there is some formaldehyde being produced, but it gets detoxified. but if there is increased amount of oxidative stress present, then there is an accumulation of formaldehyde in the plants. So what that shows us is that oxidative stress, if it is not controlled, may lead to an increased depletion of glutathione, and as a consequence of that, we will have an accumulation of the carcinogen formaldehyde in the plants. So again, we did a sensitivity analysis to make sure that our results make sense. We again and again found the same results for both glutathione as well as formaldehyde. And in the next paper, we wanted to see how the genetic modification is changing or affecting these molecular systems. So we talked about the human metabolism and the oxidative stress. So there is some evidence that genetic modification is affecting these two processes, and we found that there are 5 ways in which genetic modification affected oxidative stress pathways. So there is some upregulation of enzymes when there was a modification in the plant. Those enzymes included catalase, SOD, GR, and APS, and these are the main enzymes that actually reduce the oxidative stress. This is called the antioxidant system of the cells. And in addition to that, we also found in the literature again that because of the genetic modification, there is an increased amount of reactive oxygen species called hydrogen peroxide. So we took all this information and we integrated that with the existing models that we already have of oxidative stress and C1 metabolism. So genetic modification is affecting, it is increasing the production of the reactive oxygen species, and it is actually adversely affecting the antioxidant system. So you have, in summary, the genetic modification is increasing the oxidative stress by increasing the species, the harmful species, as well as inhibiting the antioxidant mechanisms. So we again mathematically modeled this with cytosol, and then we also integrated the genetic modification, the oxidative stress, and then the C1 metabolism together to see the overall systems effect of what will happen if you have genetic modification. So people had seen that genetic modification can cause upregulation of formaldehyde, but they didn't know why it was happening. So we use the cytosol systems biology tool, the Bioinformatics and computational systems biology tool, to understand the existing literature, to parse through it, extract the mechanisms, and then we also use the tool to mathematically model it and predict the observation that people had seen. So some really interesting results here. As expected, because genetic modification is affecting the oxidative stress, we were expecting that it will it will increase the formaldehyde detoxification. So again, just a comparison point of view here, non-GMO plants will have formaldehyde, but will get detoxified. But when genetic modification happens, what our models predicted was that there is an increase in formaldehyde levels. So there is no, it is actually affecting the detoxification pathways of formaldehyde. Similarly for GSH, the antioxidant. So when you have, when there is no genetic modification, you have a nice steady state levels of GSH, but with the genetic modifications, as we expected, it is going to affect the oxidative stress pathways, and it is going to lead to the depletion of GSH, because GSH has to neutralize that excess oxidative stress, but then GSH is not available for detoxification. That's why we have the accumulation of formaldehyde and depletion of GSH. Yes. So that was your last paper, the fourth paper, and serendipitously we also came across this study. So these are again the continued results from our GSH paper, where we identified that we compared between organic and the transgenic plant. So in the organic, we have very very high amount of GSH, the growth molecule, whereas in the transgenic, that means the plants that have been genetically modified to withstand the Roundup Ready from Monsanto, the GSH levels drop almost 3-folds. So we came across this paper. This is a greenhouse study that a group from UK had done, where they had measured the levels of the same parameter that we had measured, the glutathione, in their experiments for organic plants as well as the transgenic plants. And as you can see, our models were validated with this new information. That means that what we were able to predict from our model actually is observed in the experimental results. So that means the mechanistic information that we have actually is close to reality. That means we were able to identify, we were able to provide an explanation of why in their greenhouse study they had less glutathione in the transgenic compared to the organic. This was our fifth paper, in which we actually simulated the same conditions as that of the greenhouse study, and we were able to match the same results. So, in summary, we were able to use this novel computational systems biology approach to integrate the existing knowledge, come up with mechanistic insights to observe phenomena. So, people had observed that there is less glutathione in the transgenic plants. We were able to provide the why behind that observation, and this is again shows the power of these kind of tools. We can within maybe almost 8 to 9 months, we were able to analyze a vast amount of literature that has been studied all over the globe and demonstrate that using this kind of approach we can understand the mechanisms of the observable phenomena. And again, one of the main conclusion was that GMO soil was not actually substantially equivalent to the non-genetically organic soil. So this is how we think that the scientific method is done, and it should be the whole question about the difference between GMO and non-GMO shouldn't be settled by the scientific consensus, but by scientific method. And I think, and we strongly think that the way that we have done can answer these questions in a very impartial and scientific manner. So the next example that I have here is about how we use the bioinformatics and computational biology tool to look at a complex disease of knee osteoarthritis. And nobody had done this before. We had to put together all the information that is available and look at the interactions in a systems view before. And this is going to be this can be a very reliable and accurate platform for discovering therapeutics. So towards that end, so if you go on PubMed again, you will find this tremendous amount of data, about 34,000 papers for knee osteoarthritis. So we were able to parse that information, and then we created this visualization tool where you can actually visualize the interactions of what's happening. So if you look at this, this is the human knee, and a knee is an organ that is composed of different tissues, including synovial, cartilage, fat cells of collarbone, and so on. And each tissue, I'll show you again. So this is the cytokine that is mostly implicated in the progression of osteoarthritis. And the growth molecule, the MB13, is one of the main molecules that creates the cartilage degradation, which is what the catabolic effect is. So if you click on that, you should be able to see the molecular pathways that exist in the current literature that link IL-1 beta to MMP13. So we were able to map out all these pathways using the bioinformatics approach, and each of those linkages actually connects to the paper from which the information came from. So this is another use of systems, bioinformatics is to create visualization tools.
And existing the current temperature that will link IL-1 beta to 13. So we were able to map out.
What's going on?
Somebody's watching the stream.
So just to get back to our agenda here is to discuss different tools that are available to look at complex data. So one of the ways that we can use these tools is to create systems visualizations like these, which will help us understand the existing literature in a very user-friendly way, which was the problem that the existing tools have.
You go back to this?
Yeah.
Okay.
So just to summarize the work that went behind that visualization tool, we had to go through over 20,000 papers. It was a global research collaboration. We actually collaborated with top scientists across several countries, almost 1,000 institutions, and this is the first systems architecture of the new osteoarthritis that allows us to use it as a platform for discovery. This brings us back to how we can use these tools to promote or further the field of vaccine bioinformatics framework. So we can, based on what I have just shared, we can use these same existing tools that we have to organize the vaccine literature, make it easy to use in terms of navigation, and have it accessible to lay people as well as scientists. And then we will also be able to aggregate and grow the existing research and explore the multiple dimensions of analysis, such as what are the effects of the adjuvants and solvents, what are the studies types that exist in the existing literature, or what are the molecular mechanisms that these vaccines are affecting. So some of the questions that we can answer using these tools is basically to get more.
I think you want to show the number of how many papers there are, Prabhakar. You missed that slide.
Okay. So as you can see here, when we type in vaccines in PubMed, we get close to 250,000 papers, which to review is a kind of a manually review is a Herculean task, and that's where the need for using the tools like what I just discussed, the bioinformatics and the systems biology tools comes into picture. These are the tools that will help us organize the vaccine literature better, allow the common people to access this information, aggregate this research to create ways to analyze this kind of literature for asking questions such as what is the effect of adjuvants and solvents, what are the study types that people have done on these vaccines so far, and what are the molecular mechanisms or the biological processes that are being affected by the vaccines.
What's the time period that all those vaccine studies are? I mean, is that ever done, or is that in a certain time period? Because I know they actually, it was only about 2010 their conflict of interest on papers, wasn't it?
Right.
So that affect.
From 1976, please.
Oh, from 1976.
Yeah, from that. It's not quarter of a million. It's 1.3 million papers.
Yeah.
That are out there. Prabhakar, you want to speak a little bit clearer? Because I don't think we can hear. Yeah, we want to go right ahead. It's about 1.3 million papers.
So we have actually created a mock-up of what this kind of visualization might look like using the existing tools that we have. So you have at the center the vaccines and different types of vaccines. So if you are going to drill it down further, for a particular vaccine, we can look into what are the ingredients in that vaccine, what are the study types that people have used to study Gardasil at the clinical stage, what are the mechanistic pathways that Gardasil affects, and what are the adverse reactions that are caused by this particular vaccine. So if you go to further and look at the ingredients, what type of ingredients a particular vaccine has, including the DNA or adjuvants or the solvents and so on. And we can go a little bit further and look at one of those ingredients and see how that particular ingredient is affecting different biological processes. For example, benzene, how is it affecting neuroinflammation? So we can query this tool to see what is the linkage between benzene and different biological processes. And then we can further go down into those biological processes to look at the molecular mechanisms involved in those biological processes and how those ingredients are affecting these processes. And that would give us the studies where all those questions relate to. So this tool also can give an advanced search option where you can type in, these would be your questions. Again, this is a first crack at this type of a tool, so any suggestions you may have to be welcome. So using this advanced search, you can pinpoint the studies that you're looking for and what information is out there or what information is not out there that needs to be studied. And ultimately, we have a list of studies that answer the questions that we have. So this is one application that we can create to look at the existing literature in the vaccine area and ask these questions, get the answers for it. So that's the end of my presentation, and I want to open this session now to the working group feedback.
There are some questions.
Before I go into the comments and questions, yeah. So, is everyone clear what's going on here? So I just wanted to let you know that this example we're giving here is just an idea, okay? We're not saying this has been built. So part of what Prabhakar wants to do is to get your interaction on how you would act. So unfortunately, the thing that we did with osteoarthritis, we've actually built that out. It's up and running. It's going to be published in Nature Medicine. But the idea is we have these tools, and the idea is you could actually do something like this, right? And the idea is when we're looking at these bubbles, there is a way to present it so it's accessible to the everyday person. You follow what I'm saying? It doesn't need to be a tech tool. It should be like you could just drill down. It could be a mom or anyone, right? You'll say Gardasil, let me look at the benzene, let me look at information, let me go to the paper. Right now, what we found was everyone in this room is probably doing their own little PubMed studies, right? You guys are all putting together, and the idea is if you did this, in the other version, which we'll probably try to get up for you before we leave, there's something up with that browser, but you can actually see we actually encourage scientists all over the world to submit new papers. This is an important point. So if they submit papers, instead of saying he said, she said, or I'm pro-vax, or you didn't cherry pick, we encourage them to put it into this repository and it gets curated. That's the key thing here. Or we can start in one area. We can just take Gardasil, right? And you can just map out everything here. And for example, if you went into study type, you said, find me all the double-blind placebo studies on Gardasil, nothing may show up. For example,
right? So you could be sitting with the legislator and say, look, let me just show you this, click, 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 see nothing shows up, or something shows up. The thought of doing this is to make something very accessible, to take all of this voluminous amount of information and organize it. And that's really the goal of it. What I'd like to do is, Debbie Nightingale, just a quick, she's a former professor at MIT. She actually wants to do her presentation now, and then we can go to all full working group. If that's okay with everyone? I want to go to Debbie's risk assessment talk, and then we can open up a full working group session on this piece and the risk assessment piece. Is everyone fine with that? Okay, I think Debbie's ready. So we can just go to Debbie saying, so we'll come back to this, but I think is Debbie ready?
I'm on. Can you hear me?
Yeah. When you want to? Okay. No, go ahead. No, go ahead. Go ahead, Michelle. Okay, I'm going to introduce Debbie Nightingale. I've known for many years. Debbie is currently a distinguished professor at UCF, but for years, since 1997, Debbie held 2 professorships at MIT, and including in the Engineering Systems Division, as well as the Department of Aeronautics. And Debbie headed up the MIT Socio-Technical Systems Research Center, and she also headed up the LEAN project, which is basically you look at large-scale systems, right, like building a healthcare system or a transportation system or a pharmaceutical system, and what is involved in doing that. So she's basically a systems person. She's written some of the 2 leading books on it, and Debbie's a PhD, master's, and bachelor's out of Ohio State and Dayton University, respectively. So let me bring Debbie up. And Debbie, is there anything else you want me to share that I missed?
No, that was great, Shiva. Thank you.
Okay, so Debbie's joining us from Ohio. All right, Debbie, so I'll click for you. Go ahead.
Okay, great. Well, hello to everyone. If I was still in Boston today, I'm traveling, but if I was there, I would definitely be joining. I think this topic is extremely important. And I will just give you a brief introduction to engineering risk assessment from a total system perspective. It's really critical to every engineering activities. And when I say engineering, I mean this very broadly. I'm going to give you a number of examples of different kinds of products and systems that are engineered, and how important risk assessment is in doing that. There's lots of courses, people make careers out of this, and there's also things, many courses at MIT and other universities exactly on this topic. So let me go through some examples, and go ahead and flip this slide. So this is the bridge, right? And so as you might guess, it's a very complex system. There's lots of parts, there's lots of processes involved in building it. There's multiple ways of designing a bridge. A lot of things you have to take into consideration. What's the weight and the loads, and what's the risk of, like the bridge being full of cars and heavy trucks and all those things. And you have to take into consideration every aspect of it, not only the things that you see in the picture, but also some things that you don't see. What kind of materials are being used? What suppliers are you using? What's the quality of those suppliers? And we often hear stories of things like things falling down in the big dig and things like that. Well, those are risk and quality issues that have to be dealt with and thought about up front. Okay, next slide. So this is now we turn to software, and we all use software, and there's a whole process involved in software design and development, as you might guess, and there's tons of risk kinds of things that are involved in that. One of the risk threats from somebody hacking into your software is the one thing that certainly companies deal with all the time. But even there's risk of like, well, what if something fails? What if it doesn't work? What if you have an error in the code? So there's in each phase of this, and I'm not going to go through these phases, but each of these phases of developing software, you're examining risk, you're modeling different scenarios, you're saying, well, what if this happens? And people actually try to, quote, break the system, so to speak, to demonstrate where the risks are and then to mitigate those risks. And how do we do that? So that's on software. Let's go to another example that I'm sure you all remember, the Challenger. In this, aeronautical engineering, which is an area that I have years of experience in, looking at risk is critical all the way through the process, from the initial concept and design all the way through how you manufacture and then actually operate and support the system that you design. And even when you go through all these different things, and I have to say, in the aero field, it's probably the most tested area of any I know, there's still disasters. And the Challenger was certainly one of those. And many of you, I know, remember how horrified we all were when it exploded, and that's when we had civilians like Christine Pollock and others that were on that flight. The interesting part of that is that there was really only one part that failed, and that was an O-ring. And it was what was a famous story about this. They've actually done documentaries and things and shared this on for leadership training, in that people at the engineering level brought this to the attention of Jeffalone, who's the company that was doing this, and say, hey, we think there's a problem with this. We think it's going to overheat. And there was so much pressure by NASA and others to make this launch happen. What it did is that they looked at it, but they didn't take it seriously enough, and then that's what caused this accident. So even when there's all kinds of risk done, there's oftentimes a lot of human error in doing the risk assessment, or not paying attention to things because you don't want to hear it and don't want to see it. Okay, next example is really, this is just, I'm not going to go through the details, but this is a typical engineering process for any new product. So you start out exploring and have different concepts, you do requirements planning, and what do I need it to do, what kind of things, and you're doing risk analysis in there, and the detailed design where you're actually doing the design, the prototyping, and building it, and then ultimately into the final phase where you verify. So you can see on this slide some areas highlighted in red where there's much more detailed risk analysis done in every phase of this. It's something that is critically important. And in fact, when you get into the detailed design, we often do what they call breadboarding on here, but it's like you're actually doing mock-ups, doing extensive testing all the way through to each of these phases. And the testing is different depending on which phase of the process that you're in. It's very important and critical that you identify the risk and then look at those areas. Okay, next slide. So to be a little more specific, there are 3 steps that in every major system we say are critical. First of all, is identifying what are the potential points of failure. So you can't do in-depth analysis of everything, so you have to identify where, through experience and through your knowledge in engineering design, where are the potential points. And I'll talk a little more on the omission errors. But then you look at potential failures, like what could possibly go wrong, and then you identify probabilities. And some of them have, very, very, very low probability, and then some of them may have a higher probability. But then you look at those and you rank them. Number 3, what are all the different systems, the structures, the component parts, the software? What's their contribution to various kinds of risk? And again, you might look and say, well, something might have a very low probability, but it's very, very catastrophic. So those are the things you also pay attention to. And obviously, if something has a higher probability, you pay attention. But it's really important to identify what's the potential impact if this part of the system fails. And I think she will get into that more as it relates to drug development and immunization issues and after I finish my piece. Okay, so let's continue on now with the errors of omission and commission. So the commission says that you include something that maybe not been tested. So it's something that hasn't been fully tested or that has had some failures. And frankly, this recent Boeing issue is one of those, where there are areas that were new, not really tested totally, we're finding out now, again, sometimes they're engineers, sometimes warned of these issues, and people didn't pay attention, right, because they wanted to get the 737 up and running, and you saw 2 very catastrophic failures with that. The other thing is what we would call areas of omission, and that's where you don't put enough redundancy in the system. And a good example of redundancy is like if you're flying in a business jet, there's always at least 2 engines. So having duplicate engines is an example of having redundancy in your system. Okay, so let's go to the next slide. So without going through this is an example in a nuclear power plant. And you can imagine how, if there's any kind of failure in a nuclear power plant, it's very catastrophic, right? So this is something where we go from left to right. It's the process of developing the plant. There's lots of potential processes and accident scenarios that you go through and you examine those and say, well, what if this happened? What if this part happened? And then you explore each of those kinds of scenarios. You say, well, if this didn't work, maybe it just shuts down the system, and okay, it's inconvenient without power, but there's other things like we saw where they actually explode and there's all kinds of problems. And a big issue here is looking at all these processes and looking at the interactions across all these processes. And what we find in nuclear is it's not just the people or the processes, the people, the parts, but it's the people aspect of it. So actually, back up one, so go to slide 10. It didn't say. Go to slide 10 now. Okay, so yeah, go ahead. Go to the next slide. Yeah, there we go. Okay, so let me give you another example. I'll pick one here in aerospace. Is that there's components. So let's say component A is the main body of the airplane, and components B1 and B2 are the 2 engines. So you can see this is redundancy. You have 2 engines, it's probably exactly the same, one on the left and one on the right. And let me give you an example here. There's all this mathematics that we're not going to obviously going into, but you can calculate the risk of failures, you can make sure that there's not issues. So interestingly, the biggest risk of failures in engines are bird strikes. And when I first heard this, I kind of actually almost laughed and said, well, geez. No, that's the #1 problem in an engine failing is a bird flies into the engine. And so they actually have big laboratories that examine this. In fact, if you go to the next slide, you can see where at the top you say, okay, what's the potential failure? Define the process. The potential failure would be a bird strike. And so then we go through and do all this analysis, and they have these actual huge rooms that have the engines running, and they literally shoot birds at different trajectories at different times into these engines to determine whether they can survive it or not. And they then go through and actually evaluate all these, and then look at things they can do to harden the engine. Like they might put in screens, or they do all kinds of different things to try to preclude this. So the process is kind of identifying the risk, analyzing it through testing, do an evaluation, and then do some controlling, like putting in screens. Okay, so I think, let's see. I think now I'm going to hand it back over to Dr. Shiva, who's going to walk you through how engineering risk assessment serves as a framework for understanding risk in vaccine development. And I think you're going to see a lot of parallels with what I just went through. And unfortunately, must leave you now, but I will be back in touch to understand how well before you come out with your workshop, and be very interested in moving this forward to the next level. Shiva, is there anything else you need to
No,
know?
that's great, Debbie. Thank you. Thank you very
Questions or
much.
anything? Okay.
Thanks. I think, so the good news is we're catching up.
Yes.
So what I thought we would do is I'm going to finish up the risk assessment piece, and then we could essentially go through get the working group working, because we'll have an hour left. If we're going to do this, to get feedback on the taxonomy and the risk piece. And then we want to cull everyone's information. The two things we want to come out of this is one work product, is what Prabhakar just went through, is to understand if we were to want to build this taxonomy of the vaccine literature, what are the kinds of questions you want to ask? And then find the gap. So that's one document or one thing we want to create. The other is, on the risk assessment side, given what Debbie just shared, what is the current flow of how people actually do risk from an engineering standpoint of vaccine development? Is Sybil on? I think Sybil's on, right? Sybil, are you there? Maybe you can make her on. So, Sybil is also an engineer. She's a quality assurance engineer, has been in the pharmaceutical world, in biomedical devices. But what I wanted to do is, I'm just going to go back a couple slides. Prabhakar, can you go back to the slides? It'll be faster there. Onto the slides where I left off with the bridge, risk assessment. And then I'll wrap that up and we'll come to this. But what we want to do is, one document that we want to create is what are the gaps between how engineers do risk assessment and how is it even done, if it's done for vaccines, and what it is. So that's one gap analysis document. And everyone, can participate in that. The second one is for people out there, mothers, working with people, how can we actually create a taxonomy that will be useful for anyone to use? And what does that look like? And what does that feel like? Here, Prabhakar is up. So I want to just finish up, tell the break, no. There you go. No, before that. I did this before, but some of you may not. Right here. Okay. So, following what Debbie said, in civil engineering, one of my master's work was actually, or pre-master's work was looking at when you get shock waves in materials, how those materials perform. There's a whole field of engineering called non-destructive evaluation. Okay. So if you have an aircraft, when you send a wave through it, and you try to understand if there are any cracks in it. Many years ago, we used to have a Volkswagen that would drive across the Marvin Bridge with radar. And you send waves and you try to predict, are there cracks? Because you don't want to open up bridges, right? It's difficult. But if you look at a bridge, bridges may have a particular failure rate, right? There is some probability that a bridge will fail. And by the way, most of this stuff, as Debbie said, is about probabilities of failure. So if, let's say, you had data that found out that there was a 1 out of 100 chance that bridges in Massachusetts would fail in a hurricane, okay? So what is the risk? And that risk is called the chance that a catastrophe would occur, or an incident would occur, would be 1 out of 100. So that's only one part of the risk. The other part is if such an incident occurred, how catastrophic it would be. Obviously, if it was in some rural area, it wouldn't be that catastrophic, right? If it was right in the middle of 93 in rush hour, it would be very catastrophic. You follow? So you basically look at the potential of a harmful outcome occurring, and then you also look at how severe that would be. And that's called a risk matrix. So on axis, you put what the potential is and what the severity is. So for example, we talk about neuroinflammation. What is the possibility that neuroinflammation can take place with or without vaccines? And then what's the severity of it, for example? Or what's the potential of someone getting a rash, right, after a vaccine? Well, that could be very high, but the severity of it can be nominal, right? You get, or you get itching. You follow what I'm saying? So different events, based on a particular choice you make in life, have different potential harm, and they have an associated probability of that occurring. So there's two metrics, the probability of that event occurring and how severe is it. Is that clear? Likelihood and severity. So you just basically learn risk analysis. Okay, seriously. Because all you do is you iterate on that. Severity and potential. So in the bridge case, the potential is 1 out of 100. How severe it is may vary where that bridge is. Okay? So if we as a society decided that we collectively, because we have this collective issue and what we want to do individually, we collectively said, we're going to spend $100 billion and we're going to go fix all these bridges before a catastrophe occurs, because we want to reduce that 1 out of 100, right? And we went and put some type of reinforcement technology, preventative measure, so it didn't occur. And we went and put these all over the bridges in Massachusetts. And suppose this occurred. After we did all this, we found out that when hurricanes occurred, 2 out of 100 of those bridges were falling apart. What would you say? What's that? It was a bad intervention. That's a good word. It was a bad intervention. But you would look at this. Now, there suddenly could be the pro-intervention people and the anti-intervention people suddenly appearing. The pro-intervention people saying this is nonsense, we should intervene, and the anti-intervention people saying, we should always intervene, right? You see where I'm going with this, right? And then the pro-intervention people would say correlation doesn't mean causation, which they're right? Just because you see this doesn't mean that intervention you did caused those bridges to fail. But in engineering, if one bridge failed in Massachusetts and one person died, what would we do? The transportation board would be called, you'd assemble a team of scientists, even if it was one person. And you'd say, we need to understand what the hell is going on. You wouldn't poo-poo that person, and there would not be an arrogance. And in fact, you would go hire the best people, you bring people at MIT, you bring people at Northeastern, Worcester Polytech, and you convene a consortium, and you say, let's find out why those bridges are failing. And you start doing modeling, there's tools that allow you to do this, and you start saying, oh, maybe that reinforcement we did, should not have been done for these class of bridges, right? Like the old ones, or the ones that were new, but you would figure out some cases, but you would apply an engineering systems approach, right? We would all demand that if we spent $100 billion. And then out of that, you may, say, what? Maybe you would personalize the interventions. For these types of bridges, the ones that were built in the 1600s, 1700s, we have to do a different approach, but you would come up with an intervention strategy from that failure. Now suppose a government said, let's say all of us had homes, and we all had moats around it, and the government said, you need to all put bridges around your home. Okay? Or you need to reinforce all the bridges around your home. How would everyone feel? What's that? You probably not feel good, particularly with knowing that you hadn't figured out this 1% or 2% thing, right? You're seeing this, and you're being imposed to spend money to reinforce your home. So that's where this collective and this individual decision-making comes. But if you had a risk matrix where you could say under these conditions, this is what you would do, it would give you some decision-making. Okay, I'm going to do that for my house because my bridge was built many years ago, and I'm going to reinforce it versus I did it mine in steel. I don't need to do it. One size would not fit all, right? If you take measles, typically, I got measles. How many people here got measles? Okay. There used to be measles parties. I think there's a Brady Bunch skit, right? Who showed that to me, Richard? Where they used to get measles. Now, when you got measles, you got fevers, chills, and rash. And this was, so if you decide, so let's say before vaccines, you got the measles, and there was probably a high risk of you getting fevers, chills, and rash. Let's say it was nearly 100%. But what was the severity of it? Was it deadly? Was it critical? Well, you probably lost some time from school, right? So maybe it was critical if you were trying to get your A and you missed, something like that. But it wasn't life-threatening. When the motivation for measles around 1963 comes because people were noticing a certain percentage of the population was getting neuroinflammation, okay? Specifically, subacute sclerosing panencephalitis, SSPE. So if you read any of the papers on PubMed, they'll always talk about SSPE. And at the time this came out, it was considered, the number that they had in CDC was 1 out of 100,000, which is 0.001%, right? that was considered too high. Someone made a decision in 63, just like the 1% of the bridge. They said, whoa, this is too high, which means the likelihood that risk was too high. Therefore, we need to start having a vaccine and we need to get it out everywhere. Does that make sense? So someone decided this number is high and to reduce the perceived risk, right? So, by the way, recently, there's been recent studies done, and some people have argued that number is not 1 out of 100,000, it's actually 1 out of 1770. So let's even bring this up to 0.05%, okay? So the justification is, okay, 0.056% of neuroinflammation is not good, so therefore we need to give measles vaccine, right? So I don't know how they decided these numbers, but let's see. This was a recent German study that came out, which means that's research that's done. However, just like going back to the bridge analogy, now people start getting vaccinated over some period of time, and then you start noticing that 1 out of 88 people start getting neuroinflammation, okay? Which, by the way, is related to autism, right? And it's the first time I'm going to only use that word because it's such a charged word these days. But you can, and by the way, these people have the HNGB1 gene associated, or the inflammatory marker. But this number is 1.136%. So you have another, just like the 2%, right, after we reinforced everything, here you're noticing that 1.136% occurrence, likelihood in the population of neuroinflammation, and prior to vaccination, people were noticing 1 out of 100,000 or 1 out of 1770. So basically, you're looking at, in the bridge case, 1%, 2% after reinforcement. We would unleash a lot of research. In this case, you're seeing 0.056% and 1.136%. Okay? Now, these numbers, people may argue we didn't get it right. Okay, but if there's some number here and another number here, this number is clearly greater if you look at neuroinflammation, the reason for measles. Everyone following this? Okay? So this is a likelihood number, but the severity of the original, so there was 2 severities here, right? One is neuroinflammation, which is very severe. I mean, it's very critical. But a rash is not so critical. Okay? So if you were to make a judgment, I'm going to go get measles the natural way. My potential, if I do that, is 1 out of 100,000 I may get neuroinflammation. And there's a definite chance I'm going to get rash. And over here, I'm going to take the vaccine. There may be a potential now of 1 out of 88 that I'm going to get neuroinflammation. What would you do? You would. I'm saying if you had those numbers, and then you could tweak those numbers if we had some personalization, right? Personal genetics, some personal history, your whole family had a history of maybe you weren't breastfed. I mean, there's different things, right? There was a cesarean birth, maybe your immune system's compromised, but you would tweak those. But this is a way you would make rational decisions. The same way you decide whether you're going to let your 18-year-old drive the car and he's had 10 DUIs, okay? So you have a 200x to 1,000x increase in brain inflammation. We know correlation does not mean causation, but science demands a scientific method that we at least start researching this causal relationship. And what would we do? We would apply the scientific method, as Dr. Deonikar talked about. You would apply a hypothesis, you would experiment, you would execute, you would collect data, you mind model, you would do this process. And in the biological sciences, in particular, you would do double-blind studies, saline placebo-controlled. But as of now, at least for the 30 vaccines that are recommended for children between 0 to 18, I could not find any double-blind saline placebo-controlled. Does everyone know what that means? Everyone knows double-blind? Saline, right? So you're not using just the adjuvant as a control, you're actually using saline. And when it came to among the 30, I think one got close, which was Gardasil. But even that was quite fraudulent in some ways. if you actually look at it, because they took around 10,000 people they gave the vaccine, the other close to 900, close to 10,000 got just the adjuvant, and then a small group, around 300, 400 people, got the saline. Then the results of that study were 2.3% of the vaccine group got an autoimmune reaction. Same with the adjuvant group, 2.3%, interesting enough, and no one in the saline group. And therefore, because everyone got 2.3% of the first two groups, it was considered safe. And then they put together groups 2 and 3 together, and then the vaccine insert, they call that a saline placebo control study. Okay? So, point is that the research here, the study here wasn't done right. The other thing, given what Debbie said, if you follow the process flow that she talked about, that you go through this very important process flow like we do with pharmaceuticals. Remember I took you to the in vitro, the in vivo, phase 1, phase 2, phase 3. That's sort of the engineering process. There is, in biomedical devices, is Sybil on?
Sybil,
okay.
We have her unmuted. I don't know if
okay.
she's on.
So Sybil, so in the biomedical devices world, there is an international standard before you can, for biomedical devices. For pharmaceuticals, there's ICH-Q10, right, Prabhakar? There's a process. Interesting enough, vaccines are left out of that process. So let me repeat, there is a methodology, before you can put stuff out, but vaccines, if you can even search it, ICH-Q10 vaccines, it's like very little. It's like, we did this last night, right? So in the engineering system, so we talked about when we build standards. When you build an airplane, there are all these ISO standards. Everyone know what ISO is? ISO is the International Standards Organization. There's ISO standards for all sorts of stuff, for different processes. There's an ISO standard for example, putting out a transistor chip, how it should be processed, creating a light bulb. In every industry, they have ISO processes. There's an ISO process, I'm sure, for building a jet engine. And these are engineering processes because people don't want errors to come in. So people, tweak, and they find better processes. That's what we have in this pharmaceutical development process. We have that in biomedical devices, but I think the key thing is, in the engineering systems process of vaccine development, it's not really there. Okay? And a part of that is this aspect of the desire to do placebo-controlled studies. Now, there are comparative studies where people do vaccinated versus non-vaccinated. If you actually try to go look at what's out there, the one study that I was able to find, it basically showed that the vaccinated versus partially vaccinated, 550 people were never vaccinated, 430 people were vaccinated, and the vaccinated had the highest rates of eczema, hay fever, wheeze, and asthma. So that was the only one study I was able to find on this. And if you actually go look at other comparative studies on vaccinated versus non-vaccinated, it appeared as though this was a study of vaccinated versus unvaccinated, but it actually, if you read it, it actually showed that the vaccine was completely ineffective for workers who were trying to get influenza. So these studies, the titles don't, if you actually go read them, they don't make that much sense. Now, I'm going to go over here. So the argument why they don't do the saline placebo control, everyone know the argument? Yeah. Okay, it's the ethics argument. And the ethics argument, the ethics argument goes like this, and this is actually from one of the sites. It says, if there is already a known vaccine that is safe and effective, it is unethical to randomize children into an unvaccinated group because you would be denying them the benefits of being vaccinated. So this is based on assuming it is safe and effective, but they never did a test to show it was safe and effective. Do you know what I'm saying? Now, and this is considered to be ethical reasons because you don't want to go, because you don't want to offer something that's safe and effective has not been proven safe and effective to people because you don't want to deny them access to that medicine. Does that make sense? Now, so the way I look at it is there's a number of people who attack Eastern medicine, or other alternative therapy because they say, well, you have to follow double-blind studies. So imagine if I said this. if there's already a known herb that is safe and effective, turmeric, for example, it is unethical to randomize people into a group not receiving the herb because we would be denying them the benefits of the herb. Right? Or if I said this, if there's already a known yoga posture that is safe and effective, it is unethical to randomize people into a group not receiving the yoga posture because we would be denying them the benefits of the yoga posture. You get where I'm going? And same thing, if there's already a known chiropractic manipulation that is safe and effective, it is unethical to randomize people into a group not, et cetera, all right? So what we really have here is that the scientific method is being imposed on all of these, but not here. So it's almost as though the scientific method we're picking and choosing when we want to apply it. Okay? Because we don't say the ethics argument, because some of these systems are around for thousands of years. And you almost want to say, you know, this entire statement is almost a lewd form of science. You know, and how was it proven to be safe and effective? So the bottom line is that vaccines, per the current standard, are proven to be safe and effective, and all other modalities practiced over 1,000 years are safe and effective, and do not need double-blind placebo-controlled studies. That would be unethical also. The same people who attack this are the same people who make this weird ethical argument. And so it really comes down to risk management. And this is the point before we open up. When we look at risk management, the issue is who is deciding, how do you decide risk? Okay? And who is making these decisions? And it's typically people in academia. And John Kennedy gave this very famous speech in October of 1963. He said that he was giving a speech to the National Academy of Sciences, around 2,000 scientists, and he said, you know, we rely on all of you to help us figure out answers to very complex problems, right? Because healthcare systems, immune systems, these are not simple problems anymore. And we as politicians, we as policymakers come to you, and we're noticing that, right? These legislators, many of them don't even read the bills, are relying on others to tell them what to do. So they rely, for example, in Massachusetts on the Massachusetts Medical Society to tell them what to do, which runs in internal medicine. But Kennedy made this very interesting observation. He said that assumption is based on people being disinterested in objective third parties. The assumption is that those scientists are disinterested in objective third parties. And based on that, they're going to give us the right data. And I think that's really the conundrum here. Are they disinterested in objective third parties? You know, this is actually a picture of Untitled. And this is a British soldier telling me what to do, okay? Or have we got in the world that you just listen, right? I'm going to tell you the way it is. And there is no scientific method to practice. So there's many, many questions. You know, are they safe? Have the vaccines been evaluated? Do the vaccine materials, adjuvants, you know, such as mercury, et cetera, go into the brain? Do the adjuvants go intracellular? Is there enough information to warrant their use? Are the vaccine outcomes greater than the actual disease process? Number 6, I think, is one of the most important ones that's coming out of this program. And are long-term adverse effects greater than the effects of the disease? I think what I want to do is, Prabhakar, I think we have this slide here, right? I just want to go here. Can we go, Prabhakar, do you have the slides for the risk piece? Is that?
Also on the,
Huh?
Sybil's on Zoom.
Okay, Sybil, did you want to share something with us on the 2 processes, like ICH-10? Sybil?
Yes, can you hear me?
Yeah, can you just take just a couple of minutes with your background and just let people know how the entire vaccine, you know, there's no ISO for that?
Okay, so from the perspective of pharmaceuticals and medical devices, medical devices actually, since they are marketed in Europe and other countries, they actually have a pretty rigorous risk assessment process that they go through, especially for more, I'll call it high risk products, such as like IV pumps or something that's like critical for use, or like a pacemaker, etc., right? And that's through ISO 14971. The most recent version was 2012. That's effective for the European Union. And that's application for risk management to medical devices. And they did actually develop a guidance for the pharmaceutical and the biologics. And there's ICH-Q9, and it talks about quality risk management, and that was adopted in June 2006. And then there's ICH-Q10, this pharmaceutical quality system, adopted in April of 2009. So from the quality risk management portion is as part of ICH-Q9, they talk about not really like the development process too much. In Annex 2, they really talk more about making sure that you're understanding the product performance, that you're understanding what's going to impact the quality of the vaccine or the drug, but it's not really getting more into the product safety portions. And from a medical device perspective, those risk assessments and those risk models that are developed during what they call design control, that research and development portion, they use those risk models and they're updated and reviewed generally annually. And every single time a product complaint comes in, they're using those risk models to say, are our probabilities, right, that we have in these risk models on an annual basis, are we seeing what's in the field is what's really occurring that's in our risk models. And a lot of companies are actually doing monthly reviews of their data and taking a look at those and trying to track and trying to see if the risk management makes sense. I'm not really sure how far the companies, like vaccine companies, are going with any of this at the moment, but I'm not really sure if they're actually getting all the signals either from the field. Because the product complaints or the safety information is going into VAERS, and that falls under the CDC and not the FDA, which they're two different distinct government agencies under Health and Human Services. So there could be, some information around that's causing conflict in terms of accurate risk assessment information if they are actually doing any of it.
Great, thanks, Sybil. In fact, it varies. I've read data that only 1% of the adverse reactions are even in there. The thing I want to end with is, and we open up the discussion, is if you look at this right here, if you want to apply what Debbie was saying here, if you want to identify points of failure, the errors of commissioned components in the vaccines, I think this is where we need a repository like the taxonomy. Then the issue is errors of omission. And then we would rank these points of failure according to their probabilities of occurrence. The manufacturer standard agreement, if there is an issue, let's say polymethylbenzene. And then you would rank the system structures and components, needle, adjuvant manufacturers, etc. And then the important questions we want to ask is, what is the product development cycle for the vaccine? What are the manufacturing process risk assessment protocols for developing vaccines similar to other engineering disciplines? Are these post-production risk assessment protocols for vaccines already in the market? And is risk assessment or lack thereof risk assessment the cause of the at-risk vaccines? Now, if you think about it, if we had this data that Sybil said and things were coming back, we would have these risk assessment matrices. And we want to show you an example of one. So on one axis, you have the severity, and this is the likelihood of occurring. And so, for example, this is, by the way, this is not, don't take this away, this is a fact, but this is an example. So let's say you have to choose between taking a vaccine, sorry. Did I miss the other one? Did I delete that slide? Oops, I can't delete it, sorry. Go back to one. Yeah, so we'll keep that one. Go back to the last one. Yeah. So we have the taking and the non-taking, but this is taking measles vaccine, including genetic makeup. So here we're looking at so you would do a similar slide like this for the case where you didn't take a vaccine, but here you're looking at the severity of an incident, and you're looking at the frequency here of occurrence. So you could say if you take a vaccine, by the way, you could assume it's certain that you take a vaccine. Now the certainty is a function of the same choice, right? Prabhakar, maybe you could just copy that for a second. and just we can do this sort of live here. Just copy this, and we can sort of do this as a working session here. So, and just call it not taking the vaccine in that case. So you would have 2 of these, okay? And you would do relative probabilities. You do relative probabilities. So if we go back to the first one here, so taking the vaccine, you found out, remember we said 1%? 0.01%? Well, that would mean it's certain, it's 1 out of 88 would be 1.136%. That would be considered certain relative to the next case. We're going to go to the next one. The next slide. You would put neuroinflammation much lower. Let's copy that down, okay? I'm sorry we had this slide. Let's put it rare, okay? So there is a possibility that relatively would be rare in the case of not taking, okay? Prabhakar, maybe you just want to delete all of the others, won't build this, just so people can see this in live. Yeah, just delete all those. And by the way, this is not a real thing, but we just want to do it for exercise. So how you learn sort of quick. In fact, delete these, Prabhakar. This is to start with, okay? So you would basically, if you had data, you would say, well, in this case, relative to, this is 0.001%. Go back to the other one. But in the case of taking the vaccine, we have data that is saying it's 1.136%. You got it? So in that case, your likelihood is high, but in both cases are catastrophic, right? Over here, we have, certain you may get a fever, okay? But it's negligible. Go to the other one, Prabhakar. So we put, that may about be the same too, so you put fever. But this is coming from probability, right? Which is the only way you can get this is if the data systems are working properly and you're getting this data feeding back. Because this is how you do engineering. And let's take something like, go back to the other one. Let's take something like arthritis, okay? So in the case of arthritis, the Institute of Medicine, I think, has already acknowledged that stuff like, there is a proclivity for having this. So you would probably put, maybe it's likely, or you would put it possible, next Prabhakar. And then here, it would be rare also, okay? So you would essentially build this matrix. Is everybody the idea? So, and now, this could also be tweaked based on some type of personalization. But you would literally have this, if we had access to all the data, which I know is out there, we could build these risk assessment matrices. And then you could give people understanding under what, okay, we have all the data of people who have this kind of background, this kind of genetic, or this kind of previous history, and then we can make up these things. And then it's not an issue of vaccinated or not vaccinated, it's an issue of I as an individual have real informed decision making because I have data. But this is where this leads to. This is what we call these risk matrices. Does this make sense? So, and in engineering design, there's a reason if you're at Logan and there's low cloud cover below 100 feet, right? They say the plane's not taking off, right? Because they have risk data on that. If it's a Cessna, maybe even higher, right? So in engineering disciplines, we do that. We know a storm's going to hit on certain bridges. You start pre-salting things, right? So we make decisions like this, and we do it we're getting more and more sophisticated how to do this. So I don't understand why people would not want to do this, particularly for something like the human bloodstream of human beings. So what we're going to do is we're going to go back to Prabhakar's presentation. And how are we doing, Michelle? 30 minutes? Okay.
35 minutes left completely to the
Okay.
day.
So what we, are people okay if we go 15 minutes over? Yes? So what we want to do is, we'll start with the working group, and Prabhakar will be run, I'll help him, Prabhakar, maybe even bring that up. What we want to do is we want to look, so the first thing is that taxonomy. Prabhakar, can you go to the taxonomy piece? So, do you guys think it's valuable to organize a database of the vaccine, like the PubMed, organize it in a way that's more easily accessible?
Yes.
Okay, so what we should do then is, Prabhakar, you want to go to that? Your slide where you left off with the vaccine questions. Let's keep it where we got the blue things. So the question is, if there was such a system, and we'll start taking notes on the whiteboard. If you want to, I can switch from here to Prabhakar. Yeah. If you just start at the screen. If you just start the. So if we can go here, we gave one idea, right, of what this could look like. This is an idea. So the way we wanted to ask this discussion is, what kinds of answers would you want something like this to answer? Like, how would it support what you want to do? So we can start with the working group online in here, and then we'll open it up to everyone. And if you have it, you can write it down. But the question is, it's almost looking at it inversely. What would you want this tool to answer? Right? What would you want to get out of it? We just gave an example. Sylvia, do you want to start?
So
say your name first. Yeah.
Okay, Sylvia Fogel. So basically, I think just to understand the amount of data that exists for any one topic.
So what would be a topic?
So non-specific effects of vaccines, for example, and
Okay.
or even mortality related to vaccination and mortality related to the illness itself, right? Morbidity related to vaccination, morbidity related to non-vaccinating. I think it's important to include something about the illness itself.
Right.
This is my own personal opinion, but just to even just get a sense of what data exists.
So I heard a couple of things. One is being able to quickly find illness among all 1.2 million papers, right? And then also understanding among the 1.2 million papers morbidity and why it occurred. And then in the case of vaccination, non-vaccination.
I don't know if we have the question why, but just even to examine.
Just to know the numbers.
literature that
Just to
exists.
know the numbers.
Yeah.
So basically, how many people died of this who were vaccinated and non-vaccinated, for example?
Right, or even pre-vaccine data regarding the mortality or morbidity of a specific illness. And then, post-vaccine, that's going to be very important to make this, I think, usable and open to people who are invested in the benefits of vaccination. So that piece.
Okay.
My name is Jocelyn Sam. One of my fears is how would we vet the data? Because they could all be peer-reviewed journals, but I run into the issue where certain data is not considered valid because it's 4 years old, or certain data is not considered valid because it's from a certain journal that may not be as well respected as another journal. So that could corrupt the entire data set if we have a couple journals that aren't considered valid. So I would have to prevent that.
Yes, so the thing with peer-reviewed journals, the whole process, this is like a whole another discussion. Einstein didn't publish one paper peer-reviewed. He thought the whole process was nonsense. But this is like a systemic issue, which we're not going to solve today, right? And there are papers that are wrong, and then there are papers that people are able to duplicate. So one way people do it is they say, okay, there are certain impact factors, like these journals are the best ones. But again, you can't trust that either, because Randy Schechter, when the Nobel Prize in Medicine, sort of literally right after he won it, he went and destroyed every journal. He said, I published these, but it's all nonsense, he said. He goes, the whole system's racket. It's all based on citations. So that's what we have though, So they use a thing called H factors. It's H factors, right? Where they look at a combination of your citations, how much you publish, and there's ways to do that. Typically, you bring in domain experts, but then they can be biased. So one way to do this is you almost come up with a third-party template where people read and they fill out, for example, is this paper about double-blind placebo-controlled studies? You basically, it's called curation. And then you can have people quality assurance.
Forensic nursing?
But right now, we don't even have, there's no way you can access any of them. But curation is a big process of this whole thing. Next.
I have to ask the question about the question, would such a tool be valuable for what? My perspective is, I'm Pam Gary. I've been a public health nurse for 44 years for most of that time, and the epidemiological evidence that we see, the decline, especially in the health of our children, I think there's more that should be done rather than academic application of information. We need action. And there are groups right now that are doing studies with vaxxed and unvaxxed, and they have incredible data, but none of this is publicized. If there could be a network of groups sharing information, I think it would be more relevant. But to have a database with information, how is this going to change the outcome of what we're seeing right now?
So the question is, even doing this doesn't really help anything, does it really help anything? Right? So one thought here is, when I looked at this, is that you have people who are what you call the pro-vaxxers, who just say you should vaccinate across the board, and then you have other people saying you should not vaccinate. And then there's, I would say probably, I don't know what the percentage is, a number of people who don't know what's going on, what I call fence sitters. We're watching it either way. And in any argument, there's always the resistors, the change agents, but the majority of people are fence sitters. Something like this, being the transparency and the openness of it, I think, affords the fence sitters an opportunity to see who actually wants to do science and who doesn't. There's a value there in terms of enabling people to say, look, we want to actually build this, we want to show that there's no double-blind placebo-controlled studies. I make out of that. So one thing is, if you want to move the needle, if it's people in their own echo chambers, that's one world. The other is there's a broad set of people who don't know. But imagine if you had a tool like this, you could say, look, click, very simple. A child can use it. You see, there's not one placebo-controlled study for arsenal. Do you see that? Among all the 1.2 million papers. So the thought here was that you could use this to interrogate, albeit there could be inaccuracies, etc. Even with all of that, even with potential manipulation, that you find these big gaping holes, and then it becomes a communication tool. But maybe you're right, maybe that's also valuable. But that's why we're holding this, to find out if that is valuable, maybe this isn't worth doing. Yep.
I think.
Let me just finish with the working group.
Sure.
And then, yep.
Oh, yeah, I'm Angela Walker, I'm a I would look at the risk assessment. I think that with all the examples you've got up, bridge building and everything else, all the people responsible for that, if there was failure, would be held accountable. There would be liability somewhere. The vaccine program, there is no liability. There's no one really to invest in the safety of it, or maybe there would be much more risk assessment. Everything you're saying would be done if they were held liable for any of these damages.
Aaron, you want to say anything to that, or you want to talk about that right now? What you want to say? Not yet. Okay.
I would agree that when you have a product on the market, it certainly helps when class action attorney and product liability attorneys can place liability back on the manufacturer. That drives safety, that makes them more concerned about their bottom line with regards to safety. When you've taken that away, obviously you've taken away certain incentives to assure safety. I think that kind of speaks for itself, frankly.
Let's focus, before we go to the risk, on the taxonomy piece. What are the kinds of questions you may want to probe this database? But to Pam's point, do people think that this database is just maybe not even a good idea?
I think it's a good idea. It's a great idea. Incredibly useful.
Okay.
It's a good start.
I mean, advocates need a place to have, and researchers need a place to have the data accessible without having to do personalized search every single time. And it's so visually appealing. The osteoarthritis example is so visually appealing. I think it's a better job.
Jen?
When I attended your health lecture a month ago, it was my question, because it's the number one point of confrontation with my husband and I, of not having the tools as a mom. And so, as a mom, I need the tools to show people that I can read and I can look at research, and that there is, in fact, no true safety study. Because people just think that there's a safety study, because why on earth would there ever be 70 vaccines recommended to children without safety? So it's this huge sense of false hope and security, I think, for the average mom. So, moms need a tool for something to start that conversation.
Well, you know what's interesting, what you just said? There's a lot of data on the short term. I think Allison was saying what we do on the short term.
Yeah.
This is a gargantuan project. One thing we could do is among this whole network is to focus on safety. So you could say, of those 1.2 million, let's find all the papers that have to do with safety, and then organize that into a taxonomy. There's various lenses, but because you say you're arguing with your husband, the assumption is that you're safe. So if at least you can take it from the angle of safety and say, out of those 1.2 million papers, there's 200,000 on safety, or 50,000. Then of those 50,000, there's safety work on these different vaccines. So you almost start with safety, then you can go to the vaccines and then you can look at the different study types.
Yeah. I delivered my son down the street at Mount Auburn, and I got into a, debate with the midwife, because I'm like, well, go get me the pamphlet insert, right? Because she was like, where are you getting all this information? I'm like, I'm reading the pamphlet insert. There's no safety study, on DVAC and flu vaccine for moms. And so it's just, as when you are going into labor, you're fighting doctors and nurses wanting to have, doing natural things. So having a tool like this, totally would have helped me, from those arguments of, delivery of issues.
Unless you lived in California or New York, because everything is mandated now. And this database is not going to be valuable for those people. We are past the point of that being unsafe. When you get to mandation, this is all irrelevant.
Yeah, they don't care about us.
So what would be the solution then? We're going to mandate you to move out of the state, right?
Yeah.
Well, here's another solution that has been, I'm happy to tell you, it's a bunch of grandmothers who are getting together to do this, and they call themselves the control group. And what they've done is there are two jurisdictions in law: constitutional law and administrative law. In the United States, we are a corporation. We operate under corporate law. And so these grandmothers have gone to the courts and said, what would you require for us to get a declaratory relief injunction? This is something that the court would give if the grandmothers could prove that there is a danger in a corporation that's operating. And the burden of proof, once they suggested that, would be on the corporation, the vaccine industry. And they are, right now, at this moment, they are working to get that. And that will stop the they don't want any monetary relief. They want to shut down the mandates. And they could theoretically obtain that.
So why is it going to be grandmothers?
Well, we're caretakers of our species. We believe that our species is being threatened right now.
So you're saying that if a group went and basically put it into the constitutional framework versus the administrative framework?
It doesn't work in the constitutional framework. My religious rights, those are not working. We can see that. Corporate law.
Mm-hmm.
That's the proper jurisdiction, the proper language.
There's another, also, if I can add something.
This is Kelly's son. That's Kelly, right?
Yes, it is. So in January of 2020, California will have legislation that attempts to take steps towards the restoration of the medical exemption. And I think there is a legislative process that's possible that the most of us in the vaccine choice movement are very naive to. We're not political people, so we don't know our legislators' names, they don't know our names, and we don't have a presence. We're newbies. So that whole process is very much benefited by having infographics, things like what could be demonstrated easily from this information. And there's great value from the view of an engineer to look at medicine and say, as one science to another, this is what I see that's rational. And legislators are mostly uninformed. They're mostly fence sitters, and they need the education, and they're incredibly important because there's 62 people in the state of California who made the decision that we deal with now and that we hope will unmake it over time. So I think there's a lot of value to the work that's been described I'm sorry I missed some of these things, so I couldn't say how we shave it off and start the process, but I think it's a very valuable process.
Kelly, do you mind sharing? Kelly is a MD, and Kelly, you're licensed in what, Massachusetts and California, right? And you want to, it's up to you if you want to privately share what's going on for you in California.
So I've been doing medical exemptions for patients, and I'm one of the 70 doctors who've received subpoenas, so we're under investigation. And the law is written so that the grandfathering exemptions, which is a great benefit for the existing children, most of them, many of them, but they're very tenuous. Those grandfathered exemptions could be undone if my practice is declared a public health risk or if I am disciplined. So while I'm being investigated is different than being disciplined. If I become disciplined, then one or all of my medical exemptions could be undone. The medical exemptions could also be undone with the children being in a school that is less than 95% vaccinated, and that school would then be reviewed annually. So the law contains what looks like a boon to parents, the grandfathering, but at the same time several ways to give back. And it's just the intense avarice of the situation that we're in right now that has made this very strong, aggressive onslaught against exemptions that we have to deal with today.
And she said a key verse when she said, my practice would be considered a threat to public health. What we need, I think, work on is assessing the linchpin of under all this, which is the theory of herd immunity, postulated in 1938. If that could go away, none of this would exist.
Well, so Kelly also said something interesting about there's a lot of this stuff that's occurred that has not been effective with the herd immunity argument. It's been going on for a long time. One of the purposes of having this was to take a very different approach. I think when I showed that one diagram with you could go one way or the other way, I think everyone got it, right? The natural way or the other way. If you combine that with what Kelly said, you could do a very simple meme or an infographic, probably a 2-minute YouTube video. We did one on the climate change stuff. I mean, you can go look at it. It's gone to 1 million viewers now. 1 million all over the world. And we basically destroyed our support. It has nothing to do with lowering pollution. It in fact increases pollution. But it was just a drawing we did on a board, but it was a very simple engineering drawing. It's gone viral. Everyone gets it. So I'm saying the concept of teaching people a system, here's your immune system, this is how it's supposed to work, and here's the alternate way. And we try to do a simple sketch, and we have enough people that you can make this kind of stuff go viral. I think if most of these legislators are fence sitters and they see their constituents in it, you see that video, you see that infographic, there has to be other ways to do this. And part of what we wanted to do today is to give you guys a different vantage point, a different perspective. And the other piece here is one size does not fit all. That's a concept that I have not seen also come out broadly. I think the herd immunity stuff in my view has been beaten so much that by the time you explain it to someone, they don't fully get it, and they have all the arguments for it. Part of the engineering approach is you move into an engineering realm, you basically, unfortunately, for any good thing, the MD and the pediatrician gets put into a very different role. They're not the experts anymore. You're moving the expertise to an engineering process. And you're saying this engineering process on the molecular level, on the overall level, is not something that MDs, people hosts, or of course these guys are familiar with. They have frankly, they're unqualified to even discuss this. And that, I'm not saying it's the
Isn't it time to do that?
There's no time to do what?
Isn't it time to do that?
Definitely. That's why we called this thing within 4 weeks. That's why this whole thing was put together in 4 weeks, because we moved very rapidly to put this together. But I think there's some content there that could be repurposed into some very good memes or small videos that we can go make viral with some good, frameworks around it.
Just getting back to the taxonomy too, I think, this isn't just for the public and just for legislators, right? It's for, we're speaking to this, it's for physicians also. The physicians don't know this data. The opioid crisis happened not just because of the pharmaceutical industry, right? It's because physicians didn't know the data, right? And it existed. It existed. It wasn't just that, 1% of people, without medically appropriate opioid prescriptions become addicted, right? There was data that existed, but physicians didn't know it. And I think this is really important. I have spent hundreds of hours, and I'm sure other people in this room feel the same way, to understand this literature, and I still don't feel like I have it, sort of at my fingertips. And I think doing this would be incredibly important, in addition to other advocacy efforts that could be, side by side.
We're fortunate, and we got about 18 people who are some health background, engineering background come to this, but you typically don't get that many people showing up in one place on Saturday. I think the value of doing that would be, Sylvia, you could go to colleagues, right? Right now, many of the MDs and the physicians who are change makers, they don't have the tools to go to them in a very, objective way and say, look, show me a paper here. Yeah, let's, Michelle, did we get cards?
I think you have to also somehow bring up that the system is kind of a little bit flawed
Well, what I'd like to do is I want to do two parts to keep, part of it is I want to get feedback from people on the taxonomy, okay? And then we're going to go with the engineering piece. So we have someone in the audience who said post-marketing surveillance signals. We will implement, and then adverse events to be reported and or allowed parents, patients to report, okay? Yeah.
My name is Tony Pastor, by the way. I think that it would be great to help people understand study design and clinical trials and all of that, so when they're reading this data, they can understand what they're reading and what the p-value is, and that if it's a case study and a meta-analysis to sort of arm people with that data, so then they read these things, they can understand, and then they can go to legislators and know what they're talking about, and sort of go to the physician and say, here's this, I can speak your language, and that way they're not like, oh, you know what you're talking about, the invoice will put.
Right, so what we could do here is, I think one of the things Prabhakar proposed was study type. So under study type, you could have a couple other categories, right? Different kinds of study types. And you can just easily traverse that. You can go to one and say, okay, this was a meta-study, right? Or this was a clinical study, etc. So Prabhakar is going to add that. But if we could focus on this and what we could add to this, I know there's many other issues we could broadly discuss about vaccines.
I like the idea of doing individual vaccines, but I think we need to say something about issues that pertain to vaccines, right, as a whole, which I just mentioned, like non-specific effects, morbidity, mortality, but even like a category that could be combinations, right? I mean, vaccines are given.
Yeah, it's a combination.
It's why the MMR example doesn't quite work in terms of comparing neuroinflammation, because it isn't just that we're just giving MMR, right? We're giving many other vaccines, and we're making the same chemicals, and we don't know what's
So you could go regardless of the combinations, and you could essentially see when.
Or maybe, like on the other side of that big circle, like one side would be all the vaccines, individual vaccines, and then the other would be sort of combinations of vaccines, or non-specific effects over there, or morbidity, mortality. As like, so some of them would be about individual vaccines, and then some of the taxonomy would be about vaccines in general.
I see.
And some vaccines, like historically, were just vaccines that now you've got recombinant vaccines. So some of the data you'd have to say they're recombinant or
In the osteoarthritis case, when we went to different kinds of ligands, we put cytokines, growth factors, cell cultures. So you could do that before this, and then you can go to vaccines. Pure vaccine versus these combinations. That's the other way we could do it. Right, you could have vaccines, and the combinations like MMR, right, would be a combo. And then that could traverse these.
And then MMRV.
Right.
I mean, there's even like.
Right.
And the age at which they're given, like Japan, is given much later.
any other thoughts about the actual taxonomy? Jen?
I think a big piece of it too, though, is empowering moms and dads, right, for the vaccine injury, so all this information is reported, because I also would say a lot of this information is skewed, right, because not everyone's reporting it. So I think a lot of it comes from, and one of the things I'm grateful for in your movement as far as, citizen science and empowerment of the people, it's like more moms and dads have to be educated to take a stance on it.
So I think, Parker, I think the thing that you want to make a note of is Jen's point. I'm going to try to convert what you guys are saying, because it's going to go into it's basically the user interface, and the use of it is to scientists, or monitors, and families, right? It should be accessible. That's right. The way we're summarizing it? Someone says, summarize data in layman's terms that each study concise, clear info for those limited with attention. Okay, so part of it is, can you summarize? Summarization. Next one is, can we develop a system to include vaccine reactions for individuals with genetic abnormality like MTHFR? So one is, you have also the ability to look at papers by genetic abnormalities. So that could be another category or subcategory within that. By the way, everything you guys are going to do, we're going to take it and we're going to redo this user interface. So we're going to actually have an action step coming out of this. So whatever input you have, all your stuff, we're going to actually go and redo this before we actually build anything.
Shiva?
Yes, Kelly.
Thank you. There is a very small group of people who are working to write a new standard of care for vaccines that's based in science, since our existing standard of care is not based in the science. And that group, in discussing the different things, there's aluminum-containing vaccines, there's live virus vaccines, there's vaccines indicated for this. The thought we had is that the low-hanging fruit, the easiest to access and get something accomplished, is vaccines in pregnancy. And the second would be the hepatitis B for infants, because those two uses of vaccines have the least valid support. And that may be a way to look at the taxonomy too. Or maybe the taxonomy people should talk with the people who are doing the standard of care. The way a standard of care comes about is it evaluates the articles based on the Institute of Medicine criteria, and they have like A, B, C, D, and 1, 2, 3, 4 for how strong the design is, and the statistics and the different aspects of evaluating the strength of any study.
So everyone know how the IOM works, Institute of Medicine? But they once every 5 years, 3 years, they take an area and they'll publish like some study to see if the data, the studies actually pointing to some conclusion. And that conclusion they wait on. So for example, in 1999, they published a study on cannabis. And they said, well, there's really no evidence on cannabis is unsafe. In 2018, they published a study saying that we have strong evidence that cannabis is unsafe for people with a history of psychosis and schizophrenic background. So in the case of vaccines, they went through and they've done, okay, these classes of vaccines may cause this. So that's the background. So that's the Institute of Medicine. Those are the top scientists in the world. What Kelly's saying, if I'm taking away, is if you take hepatitis B and vaccines in pregnancy, that because if we're going to do this as the first prototype, we're not going to be, if we start doing everything, we may not have something tangible quickly to showcase people. So maybe we do hepatitis B, like do that. I mean, you click, there may be empty in most of them, but you take hepatitis B all the way, or vaccines in pregnancy, so now you have something tangible. And Kelly, what I'm hearing you saying is that those are good ones to do because what? Those are ones that you can make change on? That's what your thing is?
There's very little science supporting either one.
Well, that means there's very little papers, which means we can mine that pretty quickly.
Exactly. And the common sense that stands behind don't vaccinate in pregnancy and don't vaccinate for STDs in a newborn infant.
Yeah. So Prabhakar,
So, you guys see what we're saying? So if we do the taxonomy for both of those, we can have a quick home run quickly. Because two things will happen. People will use that as a reference for that case. And people say, wow, why don't you guys go do other things? And maybe we can get more people to come help us. So maybe that's strategically a good idea.
Hepatitis B also would help with mandates, right? Because it's included in most states as part of the school-based mandates. And so it would help there as well.
Okay, so hepatitis B. So between the two, which one should we go after first? Hepatitis B, vaccines, and pregnancy?
Pregnancy.
We've got to stop it.
The mandates are a huge issue right now, state by state. You know, I mean, there are bills in New Jersey, Pennsylvania, Florida, stuff, to go out of it, but, you know, I think we could do both.
I think we should do both. Now, one of the things we're going to need is when we do this, we're going to create a system of citizen science, so people can help us do the curation. If you want to help, definitely among the working group, we're going to come up with a methodology that no one can say the methodology itself was non-standardized. So that would mean people would get papers, blogs, and you go through, and you do some curation and at least the quality assurance process. Okay.
So when you think about getting the vaccines in pregnancy, what are you going to be looking for then? Studies that show vaccines in pregnancy?
Well, that's what we're talking about. Well, that's what we're saying is if you take, well,
yeah, I mean, what are you going to be looking for?
that's what we're saying. You should tell us what you would want to look for, because that would go into the taxonomy. What we're designing right now.
Yeah, but we've done that. I mean, they've only been doing it a few years. I mean, it's going to take another 10, 20 years for all the damage to come in out with children.
No. So I think what we're trying to do with the taxonomy, thank you, is we're trying to, so if you clicked on vaccines and went to polio, you would see a way to understand polio research right now. And it could be going into the study types on polio, and what Kelly and Sylvia are saying is you would probably find there's very little, but the little that's there you'll be able to categorize and understand quickly. So you'll be able to say, find me all the papers on hepatitis B that were given to children that there was a reaction. It would be a finite set that we could do, and it would be a great sort of showcase piece.
And what about discussing retracting papers?
You put that in there too.
Yeah.
So one of
they're the
the
most important ones, the ones that they saw fit to
well, that would be a category. Let's add that. So you could have a category, polio retracted papers, and then you would see the retracted papers too. Yeah.
The way you feel.
Let me just go through people's things here, because some people on the taxonomy. What about studies sponsored, funded by the manufacturer? That'd be a good one. Who sponsored? One category would be who was a sponsor. Right, so you can do find me all the studies sponsored by Pfizer. Find me all the studies sponsored by the Gates Foundation. Data gaps. Lack of study on something. Placebo control should be called as no study type. Okay, well that would be one of the study types. So if you click on study type and you went to placebo control and you click on it, it would show up 0. But you would have different kinds of study types. Please include flu vaccines, hot for kids. Okay? So another, I don't know if it's a low-hanging fruit, but flu vaccines, I'm saying.
Yeah, who collects the data as well? What agency? That would be good.
What's that?
Well, especially in Africa, I mean, the main collection.
Right, so that would be the
even if we're
sponsor of the
data,
agency, like the Millennium Foundation who's doing it. Can you give us a glimpse of the future of vaccine exemptions in the U.S.? Are we heading the route? I'm not going to do that right now. I want to focus on this. I'm going to focus on that. Comment. Gardasil flu shots are next to be mandated for New York. 2020 or sooner. Thank you for that information. Why are vaccine manufacturers such as Merck facing lawsuits? Okay, I want to get stuff on taxonomy. I'll highlight who's excluded, not included, in a given safety study. Okay, that's a good one. So what was the control groups, right? Who was included, who was excluded in a safety study? To avoid wrong assumptions publicly made. So basically, who was included in that? So if you go study type, it was adults, because a lot of the comparative ones were done in adults. Okay, that's a great one. Could there be an attempt to accumulate reactions family history, predispositions compiled as contraindications listed. So personalization. Were there any personalization variables? So if you found out these people had it, they came from this history. So you would go polio, study, and then maybe historical background. You got it, Mark? Yeah. Okay, I think the rest, hold on, am I missing, were these comments too, Sean?
It also includes how vaccines are driving virulence.
How they're driving what?
Virulence, vaccine strain causing wildlife to
Shedding.
become more, the vaccines to, not vaccines, the viruses to become more virulent in the wild.
Wild cases is not the same as vaccine.
Oh, okay, so
And the
vaccine
vaccines are
type.
driving it to become even wilder.
Right, so that would be a different class of studies is...
Type replacement?
Yeah, type replacement.
Type replacement, Prabhakar. So is is whatever the manufactured one creating more mutations?
It's like with antibiotic resistance.
Right.
Antibiotics cause bacteria to evolve to become resistant.
That's a good one.
And the same is happening with the virus.
Could we consider looking at taxonomy from different directions? Start with overreaching risks that can drill down into the specific vaccine. We can do that. You can have a different view. It's like what we did with we did pain. So you could have vaccines, but you could have it in different notes. Start at the vaccine or start with the risk and then traverse. We don't have to, like the center dot doesn't need to be vaccines. You can start, at, something like whatever, you can start with one of these. Seizures, right? Whatever that is.
There's one question There's one question I saw,
need all side effects listed. So side effects. Need age groups, reactions, deaths, and morbidity issue. Childhood, term, teen, adult, senior, that's a great one. So basically, Prabhakar categorize them. But it's sort of who was it tested on.
I think that is covered in the...
Yeah. By the way, this is phenomenal. You guys, it's good? We're getting enough feedback that I think the more feedback we get on these details, because ultimately, you're the customer of this.
I think one thing that's really important to cover is on indications for use, because there's a lot of approved indications for use outside of the package insert, which CDC continues to add all these additional recommendations. However, I would very much question all of those studies, because are they following FDA protocols, and are they following the methods of informed consent, et cetera, for approval of those studies? Who's the IRB? So I would really want to know if those are under the purview of FDA. So I'm really concerned about all these extra indications for use that are not on the package insert. And that goes directly for pregnancy, as well as expanding all age ranges on these vaccines.
So similar, are you saying that, so from a taxonomy, that would be a category of indications of use, meaning other indications of use? So the measles vaccine is just not for measles, you use it for something else?
No, what I'm saying is that, let's take DTaP and let's take the flu vaccine, correct? If you look at the indications for use on the package insert, neither is approved for use in pregnant women. So these are additional studies that the CDC has conducted, but nothing has swung around where FDA has actually approved, and it's gone through the approval process where it's been approved for marketing for these additional indications for use in pregnant women.
Off-label. It's really like pharma off-label use, right?
Yeah,
exactly.
The same thing has happened with our schedule. The schedule of vaccines that is recommended has never been studied. The combination.
How about include information about each disease the vaccines are claiming to prevent? Right? That's good for the taxonomy. If I can go through these from the observer group, I will get everyone's feedback in. What is in advance of the issue and vaccine given during illness?
Maybe they want to know.
In advance of injury, issue and vaccine given during illness.
Risk factors for injuries, that would be adversodic. Risk factors for injury, adversodics, right?
I think
We
that
don't
was
have a lot of data.
I was asking if you were collecting information on like adverse events after vaccination, what's the incidence of some other factor, for example, illness or injury or their post-op? I think that might be helpful.
Yeah, so you're saying what could be the other adverse?
Exactly. Is there anything that's in addition to the vaccine that makes things worse? Like, is there a contributing factor that makes a person more prone to an injury or adverse effect?
I think what you're saying is there sort of a, so if you're in this situation and you get the vaccine, then you're going to potentially have this effect.
Greg Poland's work is all about adversodics, right? Identifying, it's mostly about genetic risk factors, right? But the iodine cites lots of other risk factors, right? Previous illness, environmental exposure, family history, microbiome. I just don't think there's a lot of data there, but my circles would be largely
All we'll do is we'll put that, some of these things we'll add and we'll prioritize this, okay? We'll put, I just want to make sure we're going after it. We have everything and then we'll do a priority. I just want to finish up the people in the audience. Outbreaks, could each disease have a breakdown of outbreaks for the last 30 years, showing how many people were vaccinated versus unvaccinated, wild versus vaccine strain, okay? That's good. Do you think it increases in, that's the question, comment. Database safety issues, copyright, medical condition, admin, PC.
That's me. Dr. Shiva?
Yes.
On that one was me.
Can you speak a little louder?
That was me.
Yes.
Okay, so I was thinking like of Maslow's hierarchy of needs, and I put the two triangles, and the top would be the courts, then the legislature. The courts only process information, but they don't make information, and then the legislature makes the information, and then the public contributes it, and then underneath it's the person on the bottom who's affected by all of this, with the parents and the doctors contributing, the getting into the, needing the information, and then there was one more about that. But it was to frame the whole thing like that, because safety is a key word in anything in the medical practice. So if you can pose all of this information as safety risks, then it will have a powerful legal effect. So, but that was my comment, and this information can be stopped at any point by adding the word copyright. So having
we're gonna move on to the next, or let Shiva respond. We just have a few minutes and we have a lot of cards. Thank you for explaining your card. Appreciate it.
All right. I think, so to move this forward, next steps, I'm going to sort of freeze this because I think we got a lot of good feedback. I heard the summary is there's a, Prabhakar, I think if you can summarize this and rebuild this out, we can post this. We'll post this. We're going to make everything transparent. This will become version 1.0 from this work group feedback, okay? Working group. And if everyone wants to be authors on this, right, make sure you will have, if you're on the sign-up sheet and you want to be participating in this, we're going to make this sort of open signs. So there's a work group of the people who were invited, but if others want to participate, let us know. One of the things, stop by Richard and
gives your names, and you
can just say if you want to be part of the working group to build out this taxonomy. What we want to do is one of the quick white papers, the publications we want to put out. Jennifer has actually created a private group on Facebook, and that group we're going to keep adding stuff to it. But one of the things we want to do is take these notes, compile it into what's called a working group paper. It's a draft. One of the things when science open conferences take place like this, people put that into a working group format, and they know it's a draft. We'll say this is draft version 1.0. And we'll say this is what it is, and we'll continually refine it. The working group on this can continually meet, and perhaps,
you know, in short order, depending on how fast they want to move, you would come up with a final taxonomy and a time frame. You could say, like, I think what Kelly was suggesting, let's do hepatitis B, and then we get development people together to go do that. Okay, but this is going to translate into a work group document, and then we'll keep iterating on it, but it's not just going to be some theoretical document, it's going to be the requirement specification to actually go build this with a timeline for practical use. And so that's that project. Does that make sense? Yep.
I just want to add vaccine court stats into each.
Oh, that's a great one. Excellent. So vaccine court statistics. How many of those vaccines were? Payouts. Yeah. How many payouts came from that? Okay. So those are all public information, right?
The CDC has a document.
Yeah.
It's like 10 pages long.
And this Excel that Aaron shared with us, Prabhakar, that can, I mean, you already have that.
Yeah.
You know, the adverse reactions.
Yeah.
Look, I haven't seen anything like this out there. What I've noticed in being an engineer and sort of the world of entrepreneur software development, it's not you want to get it perfect, you want to get something out quickly. Speed is, because then the sooner you get something out, you get feedback.
Yeah, but then if you don't get it right, then it's hackney.
No, because we're going to say it's a draft. You always put the word D-R-A-F-T, and you tell people, provide us feedback. Part of making this transparent is anyone who's pro or against, we want them to discredit this. You want to take attacks. We should not be against that. We'll have a big feedback form. Please tell us why this sucks. And, no, we should, because that's how, tell us why this is bad, why this is good, how can we improve it. And I think if we focus the first row, if it's hepatitis B or pregnancy, and you iterate, you make lots of mistakes quickly, that's when you learn and you get something well done, and we can say this came from the community effort. I don't think we should be afraid of criticism.
No.
I think we should embrace it fully. Yeah, resilience. All right. In the next, 15 minutes we have, since Sybil is on there, the other thing we want to do is a gap analysis. This is from the engineering risk assessment side, and I think we can crank this pretty quickly. Is to say, look, here's your engineering risk assessment flow that's done in other fields of engineering. Here's what's done for pharmaceuticals, which we already know, the ISO standard, and here's what's done for biomedical devices. Where is the gap for vaccines? Sybil, if you want to you have some background in that, if you, myself, Debbie, and others want to sort of lead that working group from the engineering system side, and I think the direction that we want to go with that is, the real goal is to build a risk matrix. Like that would be the vision of doing that, and then the risk matrices don't exist, and then that's what we want to do. Again, these two documents, I'm not talking about spending like 10 years, 5 years, 2 years, like some NIH project that you can take money and then build anything. We're talking about the order of weeks to months. Okay? So the first version of the taxonomy, which Prabhakar is going to lead with anyone else who wants to be part of that, we're talking about it before the end of the year. We should get something done and start working on it. Which means there'll be something graphical like this that people can actually play with. We'll actually have a URL where you can actually go and start seeing it. The bulbs and all that, and then the document. And with the gap analysis, that will be a formal document that people can use for legislators, people can use for talking to colleagues, etc. Yep. Someone?
She has a question, but I don't know if you want me to get the card.
Yeah. Why don't you, in the interest of time?
Okay, real quick, will synopses be included in each one? Because some of these studies are, one, is really, really long, and two, some are too science-based for the average person to actually decipher. Like quick synopses of each, say, click on benzene.
Like a tweet.
Well, honestly, yes.
A lot of paywalls.
Yeah, the problem with some of this stuff is the abstracts are available, and some of the working group members have actually access to the papers, and others don't, and sometimes there's copyright issues. So, but the abstracts typically will give you a gist of what's going on. The abstracts are pretty, we could do that. I'm saying, Prabhakar, we could add a link there. If you click, you can get a little synopsis. Some of them may not have it, but people can help write those synopses. We can do that. The PLOS journal, what they do is you send a journal article there, they force you to write a one-paragraph English equivalent of it because of this precise issue that the science is funded by the public and people should be able to understand it. By the way, the NIH and the CDC and the FDA should be running something like this. They should be doing this. Yeah.
What about a short critique? For instance, if it says it's a placebo, but if someone looks and it's actually equal adjuvant, a critique could be, this says placebo, but it's not placebo, or, this is, not powering well, or something like that.
That can be done. Basically, for that particular paper, you can have different kinds of critiques. Prabhakar taxonomy of critique is the other way. So you can look by critiques and you can see all the critiques or errors in a paper.
Yeah, and see how many epidemiological studies there are. Science on vaccines, you can sort of see relative types of studies.
So that would be under study type.
Yeah.
So study type would have a subcategory, epidemic, we'll put that in there.
There is a section on the CDC website that says who should not get vaccinated. I think it would be kind of cool to, all the stuff that we're doing is to kind of go off of this order, because it would be easier for a mom to go to a doctor and say, like, my child should be vaccinated because of what the CDC is saying. Because you have this information, but then it's like, I am not empowered as a mom to apply that to my son. It's essentially just, it means nothing. But it's all
very narrow, though.
What's that?
Those criteria are very narrow, and they don't apply to like most health issues. Like
Right.
most people who have concerns about health-related and health vaccines, the CDC criteria are very narrow.
Right. Yeah, I mean, it's not helpful, I mean, if this information isn't helpful, but it's like, they're acknowledging it to some capacity, but then it's fake.
Well, they're just really limited, so I don't know that this should be based on that.
Okay.
There's more information on the website that you're talking about than what she's talking about.
Okay. So, getting back to the risk assessment on
No,
the gap
I'm
side.
thinking we're talking about the FDA's website or the CDC's website, not like the contraindications.
Well, one second, guys. So we have the taxonomy. I think he's taking care of it. Everyone cool with that? I think we have a plan on that.
Yeah.
Who wants to be on that working group? To continue that? Grace, I just want to get an idea. And obviously everyone here, okay? I assume the working group, people want to be on the working group. Okay. If you guys just tell Richard so we can get your names down, because we're going to create a group on Facebook that'll be working on that. On the risk assessment, where we look at current standards and how there's a gap, who's interested in that? Okay. Great. So if you guys could also tell, Richard, if you could have 2 sheets there.
I can give the second one.
Yeah, working group 1, which is the taxonomy, and working group 2, which is the engineering risk assessment. Well, I think in the interest of time, we're going to call this to a close, unless someone has any announcements to make. I know there's a bill, Candace, you guys are working on. Do you want to make any announcements on that?
Oh my gosh, that would like take 2 days.
Okay, that's fine. But as you know, there's a religious exemption discussion taking place here, and part of the idea is our intention from a science standpoint is to educate legislators. So these kinds of tools will help them summarize. One of the things I took back as feedback is I think Allison left, is to take that diagram we have of the IFN system and make that into something with a tangible meaning or some tangible infographic that everyone can understand. With that, leading to a risk matrix and the risk matrix is
Public health would definitely be interested, because when we have a conversation in the risk assessment portion of it, I'm actually asked you to come back and have a meeting. And we're actually going to be having a press conference at the State House as well, discussing precision medicine and risk assessments that will be coming up as well.
That's a briefing, right?
Yep.
Yeah. So we're going to be hosting a briefing, taking this back to the legislators. And one of the research analysts in public health, he was very interested in this. So I think by taking this in a different route, we also sort of lead the effort. And I think in closing, we live in a mecca of medicine, we live in a mecca of innovation, and we live in supposedly the cradle of freedom. And I think the opportunity this issue brings up, well, supposedly, right, is do we have, is truth, freedom, and Can it help in a control, or is it going to be power, profit, and control? And I think this issue is a great issue to push, that the science is not settled, and that we need to push the envelope on science. And I think if we make these tools transparent, the fence sitters, the legislators, we make it accessible to them. And that was really the intention of us calling this. And that's what we call the risk assessment conference. And I think we want to continue this and bring people over to it. Any thoughts? Final comments? Yep.
I think this is a fantastic idea. I wish we would have been able to do this in 1986 before they got my community. But we already have this in the vaccine safety data link. We already have vaccinated versus unvaccinated partially. We have the Mawson study. We have a lot of access to this. I'm glad we provide you with all these studies.
Oh, fantastic. What's your name, by the way? Where are you from?
I'm from Jersey.
Jersey?
Yeah.
Oh, awesome.
Trying to get some more information.
Okay.
Dr. Peter Abe, too. You should take a look at that.
All right. Well, listen, we are planning, and if you want to hang out, there are a couple of places that if you want to take a break. One is Summer Shack.
Yeah.
There's also Chipotle, it's non-GMO organic.
Yeah.
Okay. It's down the street. Summer Shack is a little more expensive, right?
Yeah.
Chipotle is straightforward, it's down the street, but it's not that great of an ambiance. Does anyone know elsewhere? There's a Thai place down the street. Yep.
There's that vegetarian Indian place too.
What's that?
It's a couple blocks from here, right? We went a couple times. I'll look it up.
Vegetarian Indian place?
Yeah, like a vegan Indian place. No meat.
Oh, that's in Watertown.
Oh.
There's also a pizza place. But if you guys want to go to Summer Shack, they have seafood. Is anyone interested? Everyone does. So they have a bar there. Summer Shack is a bar there.
Yeah.
So why don't you do Summer Shack? It's very nearby.
It's right next to the T. It's next to the T. I think we can
There's
stop
parking, there's tons of parking there. Yeah, so why don't we, by the way, to everyone wave. Can you do a quick thing? Everyone wave goodbye as much as you can. Anyway, thank you everyone for coming, online, offline, everywhere, listening, and to bring a close to the first conference on vaccine risk assessment. By the way, I want to just quickly, I just want to thank all the working members and all the observers who came, but we look forward to working with all of you.
I'm tired.